Good morning, ladies and gentlemen. Without further ado, we're going to begin this Q4i conference. At this time, it's my pleasure to introduce Dr. Michael Hayduk, Deputy Director of the Information Directorate.
First off, certainly would like to welcome everyone here. I'm Mike Hayduk. Not that you need to see my picture up there, but I'm the Deputy Director of the Information Directorate. I also serve as the focal point for coordinating our quantum program across all of AFRL. So it's an honor to be here today, and certainly a warm welcome to the Quantum for International Workshop. We're delighted to have all of you gathered here today at the Innovare Advancement Center, a hub of innovation and collaboration. As I said, it's an honor to stand before you here today with such an esteemed audience, and I know we're going to have a great next 3 days ahead of us. So first off, as we begin, this wouldn't be possible here in this great facility without a very strong team. Especially wanted to acknowledge our AFRL team for putting all this together. I think you know most of these folks, Dr. Kathy Ann Soderberg, Dr. Don Teleska, Laura Wessing, and John Maggiolino. They really did the hard work in putting this awesome agenda together. And then certainly our partners at the Griffiss Institute, led by Melissa Tallman and Kelly Pointer. Just thank you so much. Also, I really want to acknowledge everyone out there. I know a lot of you folks came a long ways to be here. We have folks from the UK, Korea, Singapore, other countries, and it's just a tribute, I think, to you to want to be here today, and we're really excited that you're able to join us. And a special acknowledgement to Colonel Tim Lawrence, who's in the audience today, retired Colonel Tim Lawrence, who was really, as you know, 4 years ago, was really the brains behind this workshop and putting it all together and giving us the go, and it's turned into something quite special. So this workshop represents a significant milestone in our collective journey to unlock the immense potential of quantum technology. As we convene here, we embrace the spirit of collaboration, knowledge sharing, and innovation. This workshop serves as a platform to bridge boundaries, foster meaningful connections, and accelerate advancements in our technologies that we work under quantum, including computing, networking, sensing, and algorithms, as well as timing. Today, we're privileged to have renowned experts, visionary researchers, industry leaders, and policymakers in our midst. Your presence here embodies the commitment and dedication we all share in harnessing the power of quantum technology to transform industries, shape our future, and tackle all the complex challenges facing our world. Over the course of this workshop, we will engage in thought-provoking discussions, explore groundbreaking research, and delve into practical applications for various sectors. From healthcare to finance, cybersecurity to energy, the sectors that quantum's going to impact are immense. Together, we'll navigate the ethical and security implications of quantum, ensuring responsible development of these technologies. I encourage each and every one of you to embrace the opportunity to network and connect. It's always one thing that we get with feedback is we need more time to connect and network. So we've built plenty of that into the agenda today. Furthermore, I'd like to take a moment to highlight the remarkable addition of our innovation ecosystem, and you're part of it here today in the New York State Skydome, an exceptional indoor-outdoor UAS unmanned aerial systems test facility. This cutting-edge facility, scheduled to launch in the very near future with real live flights in here, will further enhance our capabilities in the unmanned sector. Skydome, boasting a vast indoor and outdoor flight testing area, spans 22,500 square feet. It'll be the largest of this kind with the indoor-outdoor piece in the United States. As you might know, some of you might know, this is actual former B-52 hangar. So the work that went into transforming this has just been immense and remarkable. State-of-the-art facility will provide an unparalleled environment for testing and advancing UAS technologies, pushing the boundaries of what we never thought possible before. Really interesting breakthrough has been in access to this 50-mile drone corridor and the vast resources. When you put it all together, the Innovare Advancement Center, Skydome, will serve as a crucial catalyst for research and development in the collaboration of unmanned and uncrewed aerial systems. Once again, welcome to the Q4i workshop, where we celebrate the convergence of quantum technology, innovation, and unlimitless possibilities ahead of us. Let us embark on this journey together. As I said, we know we got a great week ahead of us. So with all that said, let's get down to our speakers. So please help me welcome Mr. Anthony J. Picente, Jr., the 13th Oneida County Executive. Mr. Picente has been serving in this capacity since 2006, making him the longest-serving county executive in Oneida County history. With his extensive experience in regional development and economic growth, Mr. Picente has played a vital role in shaping the progress of our community, the Innovare Advancement Center, and of course, Skydome. Innovare would not exist today without Tony's vision, his leadership, and the county's commitment to Innovare. Tony is a true friend of the lab, and certainly we can't thank him enough for all he's done here. Welcome, Tony.
Well, good morning. Good morning. It's great to be with all of you here at Skydome, and I want to thank Dr. Hayduk for a very wonderful introduction, and certainly the partnership, and Colonel Garcia, thank you for your great partnership and what we have been able to do together, and for your leadership throughout this community and throughout this nation. Great to see Colonel Lawrence as well, who was a part of all of this when we had these crazy ideas some years ago to create all of this that you're sitting in right now, and then some. And my great partner in government, Mayor Izzo, who you're going to hear from. We are just so excited about the again, Q4i being here. And for those of you who have been here before, welcome back. It's great to have you with us again. For those who are making the first trip here and the first visit, we welcome you, and we hope that your stay here is enjoyable with all of you, and that you get a little bit of a taste, not of just of what the great, and we know you're going to get a taste of what's being done here in Rome, but also a great taste of our community, and be able to be a part of that for a few days. What we have done together, obviously, this great partnership, and for us, and for me in particular, even prior to being county executive, the role of Rome Lab, of the Air Force Research Lab here in Rome, New York, has been such a driving force in everything that we have been able to do in the technology base and of our community and our region and beyond. Building these pieces out of what was the former hangar of a B-52, and now is what we call the largest indoor dome or testing for UAS in the nation, is really special to us. We were one of the first of the 6 and now 7 UAS test sites in the United States, and then back there is Commissioner Ed Curie, I want to recognize too, who leads us in this Griffiss International Airport, which has transformed over the years from what was an active SAC base to now a UAS, general aviation, international airport, and all things quantum, and all things in terms of cyber, and all of the other aspects of what is taking place here. So can't stress enough about the great partnership between AFRL, Oneida County, New York State, Griffiss Institute, the City of Rome, and Innovare here. Everything that we have dreamed about is coming true, and it's because of all of you. It's because of your belief and your investment and your time and your knowledge of what makes these wheels go. And so I want to thank you personally and on behalf of Oneida County for your commitment to everything that does take place here, and the growth that we have seen and the activity that we have seen, because without you, none of this is possible. Without your investment in coming here as a part of Q4i, as a part of this Innovare, and all things again that we are seeing happening here, could not be possible without your partnership. So again, I want to thank you for your commitment. I want to thank you all for your service, wherever it may be. I want to thank again the AFRL and the Colonel and Deputy Hayduk for inviting me and allowing me the opportunity to say a few words to you this morning, and welcoming you here to Oneida County. It's a great place to live, work, and play. Hope you have that chance to do some of that. Please enjoy your stay here, and if we can be of any help, and I can be of any help, please do not hesitate to reach out. I look forward to hearing about the next few days and the successes that came out of this great conference. Thank you, and God bless you.
Thank you, County Executive Picente. Oops, wrong way. There we go. Joining us at the same time is the absolutely remarkable Jacqueline M. Izzo, the mayor of the city of Rome. Mayor Izzo made history as the first female mayor of a major city in Oneida County, and her dedication to fostering growth, strengthening infrastructure, and creating a welcoming environment for business has had a profound impact on our local community. AFRL is fortunate to have such a strong local partner in Mayor Izzo. She's a great colleague and obviously a true friend of the lab, and her support has been remarkable throughout the years. Mayor Izzo.
Thank you, Mike. Good morning. Great to see everyone here. I've come to all of these conferences. I was even on the virtual one, I think. And, you know, the county executive is very modest. When we came up with this crazy idea of how we wanted to build out some of these facilities here on the airport side, he lobbied the Board of Legislators for multi-millions of dollars to do this. And we're very proud of this facility, and I think it's a great venue for this conference. We are leading in quantum, not we, the lab. We always say we. Colonel Garcia and Mike and their team. But you know, quantum is going to lead us into the future, and you all are going to be such a part of that, and to think that we're doing what we're doing in those spheres here in Rome, New York is really remarkable. I hope that over the course of the next few days, you're able to network and really collaborate on these quantum issues, but in this environment that we've created here with Innovare and the Griffiss Institute, there's just so much that can be done here, and we hope that you come back, and these spaces are always available. You might be in town, you might want to stop here and use the facilities. That's what we're here for. And I know that all of you are interacting with the lab, and that brings you in and out of our community quite often. Hopefully, too, while you're here, during your stay, you're able to get out a little bit and visualize and see what the community is all about, maybe take in some of our restaurants and some of our activities. I know you'll be very busy, but we are here to welcome you, and we want you to have a wonderful time. And hopefully, there'll be groundbreaking issues that come out of this conference. And I wish you all Godspeed for the next several days. And if I can do anything for you, as the county executive said, that's what we're here for. Please contact me if you need anything ever. And if you're in our area, please stop in. I'd love to see you. Thank you, and I hope everybody has a wonderful conference.
Thank you, Mayor Izzo. We are privileged to have here today Colonel Fred E. Garcia, the Director of the Air Force Research Laboratory, Information Directorate, and Commander of Detachment 4. Colonel Garcia leads the Directorate's efforts in exploring, prototyping, and demonstrating high-impact, game-changing technologies in C4I and cyber, command, control, communications, computers, intelligence, and cyber. Colonel Garcia oversees a total workforce of over 1,200 government, military, and on-site contractors, and is responsible for the execution of an annual budget of over $1.5 billion. He is a true technologist at heart. He's a strong supporter of quantum technologies, and we're very fortunate to have his leadership at the helm of the lab over the past 2.5 years. Colonel Garcia.
Well, welcome everybody to Q4i. I think actually the mayor, I have to correct you because I think you were right the first time. It is a we. It's not just a lab, but it's we together that makes this stuff work. Yeah, we've got some cool stuff over there, but we couldn't do anything without facilities like this or without the partnerships. I was just talking to Congresswoman Stefanik's staff about some of these kind of things, and I had to highlight again the fact that the partnerships are the only thing that make this work, and it's not just we have a lab across the street and there's one here and then we have this facility and partnerships like that. It's partnerships that you guys are all doing together to actually make this technology work. We've seen a lot of folks doing some things across the the world, a lot of different types of quantum technologies. There's a lot of different types of approaches, but that's kind of the big collective we. We, us, you guys are all working together to try to figure out what's the future of the quantum stuff. That's why I'm really glad that Colonel Lawrence is here, because I'm not even qualified to carry his bags. He was the one that got all this started. He's the one that really knows the nuts and the bolts of this stuff, but you all know the nuts and the bolts of this stuff too, and so I hope that that really works. But the ecosystem that we have in place, and Mr. Picente, you talked about this a little bit, the ecosystem that's here in this Mohawk Valley is unlike anything I've ever seen. And it all goes back to the partnerships, and so we've got 3 Congress people that support everything that we do here. Stefanik, Tenney, Mr. Williams, County Executive, the Mayor, all the local folks, the Assembly people that work behind the scenes, the State Senators representatives. They all work to actually make this place happen, and so you're in a very unique place here right now to do some really good work that you'll never find anyplace else on the entire face of the earth. I haven't been every place on the face of the earth, so that's probably a bold statement, but I think you'll find that this is really unique, and so I welcome you to come here and be innovative and be ingenuitous, where that word is. Colonel Lawrence will come and kill me after the fact. Go get my bags is what he'll say. But with people like Dr. Hayduk and all the folks that are here, I hope that you enjoy this, but I hope that you put all of your collective thinking minds together in the collective we to actually figure some stuff out. And if you ever need anything, let us know. We're just right across the street, but we're here, and Dr. Hayduk will be here. Any questions from you guys right off the bat? That's probably a bad thing to do, but we'll be around, and so welcome. This is a great place. I hope you do great things. Thank you.
All right, great. Thank you, Colonel Garcia, and everyone for their welcoming speeches this morning. This is just a great way to kick off Q4i. So we're going to begin now with our official program, technical program, and we're going to welcome our first keynote speaker, Dr. Jamil Abo-Shaeer, the CEO of Vector Atomic. Dr. Abo-Shaeer's expertise in quantum technology acquired through the years has been in industry, government, and academia, and has led to the development of quantum-based clocks and inertial sensors with diverse applications in navigation, telecommunications, climate science, agriculture, and geophysical exploration. Welcome, Jamil. Down arrow works, and take as much time as you need.
Everyone can hear me? Correct, great. All right, well, thanks everyone for being here, and thanks to the organizers for inviting me. I'm Jamil Abo-Shaeer. I'm the CEO and co-founder of Vector Atomic, and today I'm going to talk about developing real-world quantum technology. Okay, so we've all heard, presumably in the news lately, there's a lot of interest and excitement around quantum technology. And a lot of that centers around quantum computing, which has quite a bit of promise for what it might enable in the future, but quantum technology has already arrived, and it's arrived through things like atomic clocks, which enable GPS. So our transportation, telecom, financial, defense sectors, all are fundamentally reliant on GPS. They can't operate without it. It's generated more than $1 trillion in economic impact in the US alone, and it's estimated that the loss of GPS would cost $1 billion a day in economic impact. It's surprising, it seems like. Even more than that to me, probably most of us wouldn't have been able to find the place without it today. So GPS is enabled by 1960s atomic physics, atomic clock technology, and what we're hoping to do is develop the next generation of atomic devices to enable that GPS 2.0, next generation type stuff, and hopefully unlock that next trillion in economic impact. That's not going to be in atomic clocks, but it can enable quite a few applications, things like very high resolution GPS for things like autonomy, high bandwidth communication, mineralogy, oil exploration. So the laboratory devices already have the performance necessary to meet these applications. The issue, and I'll show a little bit more about this, is that they're enormous, fragile, and expensive to build and operate. If we want to build commercial devices, we really need to focus on things like integration, operability in the real world, reliability, and cost is a big driver too. So at Vector Atomic, our focus is on operationalizing atomic technology for navigation and timing. Just a little bit about the company. We're a little over 5 years old. We were founded in 2018. We're currently 42 employees. We're located in Pleasanton, California, in the Bay Area. So a bit of a trek to get here, but I'm certainly excited to be here. We were, a little bit different about our company versus others. Certainly in our area, is we're funded exclusively through competitive government R&D contracts. We have no outside investment or debt. We're even a little bit profitable, which is novel for a quantum company. Our focus right now is on fielding pre-production units, getting them out in the world, exposing the wart, seeing what they can do, with the idea that we'll start rolling out commercial products in the next year or two. So what you see here along this strip of images, this is our current Hall of Fame. None of these things make it on here unless they've gone out in the world and they've done something useful. So these clocks, synchronization modules, and this atomic gravimeter are all offering state-of-the-art performance for their form factor. And we've really tried hard to take this hardware out and operate it on land and at sea. And that atomic gyroscope will be going into space hopefully soon. So in that vein, we took part in the Alternative PNT Challenge at RIMPAC 2022. This was a multi-nation demonstration of quantum technology. Let's really see what we can do with this technology. So this is a Five Eyes effort, all the English-speaking countries, and the US POC was Tommy Willis at ONR. So here we delivered multiple devices. We brought aboard 3 optical atomic clocks and an atomic gravimeter, and I'm going to talk about each of these in detail a little bit later on. But the kind of punchline is we're able to operate with higher performance than the clocks that are currently operating on these Navy ships, and we're able to generate high-resolution gravity maps that match what we would see from our satellite gravity maps, and that can be very important for navigation in the absence of GPS. So what's all the excitement about these atomic sensors? Well, laboratory atomic devices have unmatched precision and accuracy. This strontium lattice clock that you see here is good to a second in 50 billion years, 4 times the age of the universe. It's the most precise measurement device on the planet, bar none, and we can use a lot of the same tools and techniques to build best-in-class inertial sensors and electromagnetic field sensors. I think because I know there's a lot of excitement about quantum computing, I think there's an important note that these devices that we build in the lab have a lot in common with neutral atom and ion trap quantum computing, and a lot of the people and resources are shared between these labs and are common. So great, these things have amazing performance. What's the catch? I think if you look at the pictures, it's pretty clear. These devices, I would call them quantum Rube Goldberg machines. They are incredibly impressive in terms of performance, but they're poorly integrated, they're fragile. They don't operate for 50 billion years, they don't operate for more than a couple hours on their own. They're babysat by a small army of grad students and postdocs. So at this point, the performance is good enough, and if we're going to build commercial devices, we really need to focus on things like integration, operability in the real world, reliability, and cost is also a big driver. So there's been some very nice efforts to kind of initially to get this technology out into the world, and I would call this kind of lab-in-a-box style integration. And that's to take what you have in the lab and basically wrap it up, re-engineer it. And these devices are definitely better engineered versions than their laboratory ancestors, but they retain a lot of the complexity, reliability, and cost of their laboratory ancestors. So these current devices, if you look at them, they're really hand-built one-offs, and the build costs are anywhere from $250,000 to $1 million per axis. So what we learned from this is miniaturizing the components is insufficient. We really need to think about how to re-architecture these devices. So our goal at Vector Atomic is to manufacture these devices in the tens of thousands. We're not doing that today, but we hope to get there. And what you'll see is that requires a lot of planning from the outset. You really have to design straight toward that goal of something that is manufacturable in large quantities. So here is some of the existing high-performance clocks and inertial sensors that you can buy today, divided by device class. Characterize the first as lab-in-a-box style, and that's things like the maser, which are incredibly important to our world's timing system, but fairly large and expensive systems, anywhere from $300 to $500,000. Smaller kind of chassis scale integration, things like cesium beam clocks and ring laser gyros, and then very well integrated systems, tactical devices like the microchip CSAC and very small ring laser gyros that go into things like JDAM. So if we look at the market for these things, and I know that not everyone's interested in the market, but we want to build things that are sustainable and that people will be interested in buying and fielding. The punchline is if we build expensive devices, we're going to sell 10 of these a year. If we build cheap devices, we can sell tens of thousands. And luckily, cheap doesn't have to be $5. Cheap can be tens of thousands of dollars if you look at this plot. So this is just taking all those devices that you saw on the previous slide and showing what their estimated yearly revenue is. And not surprisingly, you make something smaller, you make it so it can go in more places, and the markets will be larger. So cost must be a design consideration from the outset. You really need to shoot for 100K scale devices, not $1 million scale devices, and then try to get down to something that can be $10,000. Luckily, there's precedent for this. You can follow the lead of similar high-precision devices. So you're seeing pictures of ring laser gyros, which are used in things like the planes that many of you, commercial aircraft that you flew here this week to get here. So they started out as relatively large lab-in-a-box style devices, but slowly they've been integrated down into highly integrated, fully customized designs. So if you want to build cheap devices, you really have to build them quickly and cheaply. You have to build them with the size, weight, and power and the dynamics that are compatible with the application you'd like them to operate in. And you need them to operate turnkey. You can't have a PhD atomic physicist come along for the ride. So when we look at this, we think these devices really need to be designed from the ground up. You need to purpose build them, simplify the architectures, and make performance trades. Our philosophy is 100K scale devices are achievable with conventional components, but if you really want to push down to these $10,000 scale devices, you can sell in the tens of thousands and really deploy wide scale. You need to develop custom components and manufacturing techniques to go along with those designs. So what's the guts of these systems? Quantum hardware is really built from classical technologies, and there's three things: vacuum systems, lasers and optics, and electronics. So if you really look at the core of these things at the guts, it's a metal and glass cell that we use to isolate the atoms to separate isolate their quantum state from the outside world. They typically have a window into which we shine laser light that allows us to prepare, probe, and read out the atomic state. And then electronics and software orchestrate this whole kind of precise measurement sequence. So given this goal of building devices in the tens of thousands, we have developed a lot of this technology in-house. Ultimately, the things that you're going to see that we've put out into the world are in this top row. They're kind of fully customized systems built from off-the-shelf components, but we're also in parallel working on cheaper devices where we fully customize the systems and fully customize the components. So if you want to build something that's a full system that's ultimately small, low power, all this, low cost. You can't just choose one of these three areas to work on. You really have to work on all three. So that's what we've been doing for the last several years. A lot of this happened, you know, in a very challenging environment during COVID. The company has kind of been brought up, you know, through that time, but you just kind of got to grind through. We all have the same challenges to deal with. But, you know, here's our attempt to really redesign this quantum hardware from the ground up. So starting with small SBIRs, we were able to do some initial concept validation of the technologies. Based on that, we were able to win projects to build up subsystems and demonstrate them on the tabletop, show good performance, and that got people interested in contracts that would allow us to do system integration, really build out the system and take it out in the world. And we're excited to now be working on manufacturability of these systems as well. Let's start this. Okay, so the first topic I'm going to talk about today is enabling operation in GPS-denied environments, and that's by deploying atomic inertial sensors. So as an example, and what motivated this project, submarines use inertial navigation to maintain stealth. They don't want to use things like sonar, which can give away their location. So they'll work hard not to emanate any signals, and so they'll use an inertial navigation system, which is 3 gyros, 3 accelerometers, and basically integrate up those equations of motion to provide their position over time. And they might be underwater for as many as 30 days. This inertial navigation system, the position error will grow unbounded over time if it is truly free inertial. And really the best kind of strategic grade INSs may accrue as much as a kilometer of error in 2 days. And so no surprise, after 30 days or after 90 days, you might not know exactly where you are, and that can cause problems. And this is an example of that, where this submarine hit an undersea mountain. So there are real challenges associated with this. We'd like a way to be able to improve that navigation error. So this is a project that was guided by Office of Naval Research, and their interest was in doing navigation aiding by measuring local gravity. And the idea for it is relatively simple. You take a standard inertial navigation system, which will have error that grows, you know, unbounded over time, as I mentioned. And if you take in additional signals, if you measure the local gravity of the of the seafloor, you can use that information along with satellite gravity maps to feed back to your system and correct that navigation error and maybe bound the error at a much lower level, hundreds of meters. So the idea is that the gravitational texture varies on kind of 100-meter length scales by about a micro-G, a part in 10 to the 6, and that's what you're trying to measure. In this project, they wanted us to do that in a form factor that was compatible with a UUV, something that could be small, and that means the sensor must be rigidly mounted to the platform. It operates in what's known as strap-down configuration, so there's no motion stabilization or gimbal. You just bolt this thing down. It's got to measure the local gravity. So you'd like to be able to measure that gravity, like I mentioned, at a part in 10 to the 6 over these 100-meter length scales. That performance is easy in the laboratory. You can measure nano-G levels of gravity in the laboratory. What is very hard is to do it in the presence of motion, where you might be on a ship and local gravity, or the acceleration on the ship might be about 1/10 of local gravity. So you have this background that you're operating on, and you need to be able to pull out a signal at a part in 10 to the 6. And just to kind of give a visceral feel for what that looks like, this is a ship that we operated on where we had to do exactly that. Put this gravimeter on, and despite all this motion and all the turns and the twists and the banking and the heave motion, be able to pull out these kind of microscopic changes in gravity. And that's a real challenge. So This is the system that we built to do this. It really is purpose-built for exactly this application. So it's trying to address these real-world challenges of operating under dynamics, operating in a real-world environment, doing it at low size, weight, and power, and operating autonomously. And so you can see kind of the guts of our system. The first is this hybrid atomic sensor, which really allows us to operate under high dynamics. Typical lab-based sensors might be able to make a measurement once a second. We need to make 40 measurements a second. To boost that bandwidth, we've also integrated with a conventional accelerometer. The laser system that we built this from is a telecom doubled 1560 laser system. It really allows for very robust operation, and it tethers over that sensor through a single fiber. Let me see if I can, yep. Control system, when we built this, we were a bunch of physicists starting out, so we just built an off-the-shelf control system with some custom electronics. But we've developed in the meantime, we've built up our electronics team, and we have a purpose-built electronics system built under a parallel project. So in terms of specifications, can this work? Let me turn this on. Here's the goal for our system. Basically, that ship will traverse 100 meters in 10 seconds. So in 10 seconds, we need to be able to measure these micro G, or in this case, milligal, it's a different unit, fluctuations in local gravity. And then we need to basically do that for all time so that we can compare it to these local gravity maps. So that's what we're doing here. You can see this hybrid measurement, what our system is capable of doing, so it can meet the requirement at 10 seconds, and it's able to hold it effectively indefinitely. Just in terms of making these systems robust and reliable, not a lot of good came out of COVID, but when we started this project, we had the sensor built, and we got it networked up, and one of our physicists just sat in his apartment, 50 miles away, and just developed a bunch of optimization routines, calibration routines as well for sensor bring up, and so that allows us to really basically flip a switch and get this thing started in 15 minutes. We've operated this thing for multiple days, multiple 30-plus day runs, so it operates fault-free autonomously. We've made up to 100 million measurements without a fault at a 40 hertz duty cycle. So great, this thing works in the laboratory, but can we take out into the world and do what we hope to do with it? And so this is the first kind of demo of it. We took this sensor, and you can see all the pieces here. You can see the inertial navigation system, the sensor head, the control system. Loaded it into basically a glorified shipping container provided by ONR that has power and AC, and we loaded it onto the deck of this ship. And we did 2 tests of this. And so you can see that here. We did this initial demonstration above the Point Sur in February 2022, and this demo for RIMPAC in July of 2022. And what's kind of the punchline for this? Well, we were able to bring the thing up quickly, get it operating in 15 minutes on both ships. For the duration of these measurements, there was no physical interaction with the sensor. Really, the only downtime was due to a planned calibration and Windows updating itself in the middle of one of our runs. So we all have that problem. Gravimeter had 99% uptime for both underways, operated for 100 plus hours out in the Gulf of Mexico and 500 hours in Pearl Harbor. And the dynamics were much worse, in some cases than what we designed for. We saw pitches and rolls of 15 degrees, pitch roll rates of 8 degrees per second. You saw the video surge and sway and heaves of a quarter of gravity. So that's a very challenging environment. Can you pull out that measurement that you need? So here's our measurement of the gravity anomaly. For this gravimeter, we used a local gravity map based on satellite altimetry, and you're seeing the residuals here in red for our atomic gravimeter. This we were able to recover this anomaly. This is great piece about atoms. We just used some pre-calibrated alignments. and offsets. There's no free parameters in the system that we used. This is the measurement that came out of our system. It agrees very well with the best satellite altimetry gravity maps. The difference is on the order of the error between competing maps. So we are able to measure local gravity on the time scale and at the sensitivity that we need to, and preliminarily these results have been shown to reduce the navigation error like we ultimately had hoped they would. So the work continues. We did our first road test a couple weeks ago in preparation for another at-sea test. We're going to be doing this summer above the USNS waters. To our knowledge, this is the first road-based atomic gravity survey under motion, 100% sensor uptime, despite temperatures reaching as much as 105 degrees. That says C, that should be Fahrenheit. It certainly wasn't boiling in there. That's a last-minute error on my part late last night. We drove around, we visited 10 USGS surveys to get an absolute comparison. Sensors operated through aggressive dynamics and a rough thermal environment. Data analysis is still in progress, but the results match our expectations, so that's looking good. See how I'm doing on time. Okay, the next piece I want to talk about is global scale synchronization at picosecond levels, and this is really can be enabled by deploying optical atomic timekeeping technology. So as I mentioned earlier, GPS is enabled by atomic clocks. Here's kind of a schematic of how it works. There's a bank of 70 cesium clocks, 20 hydrogen masers, and 6 rubidium fountain clocks at the U.S. Naval Observatory. And that master clock, through two-way RF time transfer, updates 30 GPS satellites, which are carrying 3 rubidium clocks. And those clocks orbit at a period of about 12 hours. So because of that and because of the performance, which I'll show in a second, global scale synchronization is really currently limited to nanosecond levels. Again, just a quick schematic. A satellite updates itself to GPS at the nanosecond level, and then as it orbits, it accrues some timing error, around a nanosecond in 12 hours. And then through GPS one-way time transfer to all our devices, we're able to synchronize at kind of the 10 nanosecond level. Our goal is to upgrade the world's time base from nanoseconds to picoseconds. That's an ambitious goal. It's not going to happen tomorrow, but we need to take steps to do this. So by going from microwave systems to optical systems, we can really push performance. So in this scheme, it would be two-way optical time transfer from the master clock to the satellite. That can be done at the 10 femtosecond level. As these optical clocks, which are higher performing, as they orbit, they'll accumulate less error, anywhere from 100 picoseconds to maybe even down to 10 picoseconds, and then use some similar satellite two-way time transfer to synchronize at this 10 picosecond level. So why should we care about that? Well, if we want to do things like RF coherence or very high resolution positioning, you really need higher performing clocks and higher performing synchronization at the sub 10 picosecond level. So if you want RF coherence at the 10 gigahertz level, yeah, you really need to push up the clocks. That can enable, in terms of RF, if we can coherently link our receivers and emitters, we can reduce the individual power burden on each of them, really improve performance of the aggregate network for things like multi-static radar, coherent antennas, and space-based imaging. So in order to have RF coherence, it really requires synchronization at a small fraction of a wavelength, lambda over 10 roughly, which translates into some pretty aggressive numbers as you push up your frequency. So at a gigahertz, you need to know your timing, or you need to be synchronized to hundreds of picoseconds to maintain coherence between receivers. If you push up to 10 gigahertz, you need to know that, or you need to have your time synchronized to tens of picoseconds. And that will also give you positioning at the 3 millimeter level. So if you look at today's commercial portable atomic clocks, You can see they do support this nanosecond timing. So again, things like these cesium clocks and the GPS clocks can hold nanosecond timing for tens of hours, but certainly can't hold picosecond or 10 picosecond level timing for very long. So the goal with these optical clocks is to push this performance higher to really enable these kind of next generation applications. So we did a lot of work to build up these systems, and we built 2 of these optical atomic clocks. We took them to NIST and tested them for 30 days versus NIST timing standard. And here's the performance of those clocks. So you can see we really can kind of push to higher performance and support these kind of next generation timekeeping challenges, things like 10 gigahertz coherence. We're able to hold 10 picosecond level timing error for more than an hour, and typically that would be done for less than, say, 20 seconds with the current devices. So we built these things, we took them to NIST, they operated in a stable environment. How will they operate in the real world? So also, we also took these devices as part of that RIMPAC challenge. You can see we boxed them up, shipped them through FedEx to Pearl Harbor, unboxed them, put them in the system, kind of got everything up and running in an hour or 2, and then they operated on these ships for weeks. And so how do they do versus how they operate in a benign lab environment? You can see that that's the open circles. So the timing error accumulated is basically the same as what we saw in a laboratory environment. So the clocks operate with little degradation at sea. So that's exciting. So there's 2 pieces to this. There is the timekeeping, and then there's also the synchronization of those clocks. You need to have both to realize these kind of picosecond level timing networks. And so we have also developed femtosecond level synchronization hardware based on a technique that NIST has developed over the last several years, and we collaborated with them on this free space 2-way optical time transfer hardware. Our focus was really on improving you can take a look at what they've built, and it's an awesome system, but we really wanted to work on improving the integration and robustness of those systems. So we built, basically robust versions of the guts of their system, frequency combs, all the optics, the electronics integration. Another big piece of this in terms of kind of re-architecturing these systems is we moved where we could toward photonic integration of these systems. So one of their pieces, basically the measurement unit, this heterodyne fiber spool, we were able to kind of take all that and integrate it onto a photonic integrated circuit. And that really minimizes the fibers, the components, and allows you to put it in a compact package and stabilize the temperature, which can actually make things more stable. So we took these devices over to NIST and we operated them on their 30-kilometer free space link with, we weren't sending through kilowatts of power through this free space link. This was at picowatt scale. Got these systems integrated into the system, and you can see the results here in terms of what the performance is. This is this synchronization level over this 30-kilometer free space link, so we're able to synchronize these devices at the 10 femtosecond level. So again, supporting that kind of picosecond level timing goal. So that's all I have today. I'm happy to answer questions about any of this work. I definitely want to thank our team and the sponsors and all our collaborators who helped with this work. It was a big effort, and it's been a challenge over the last several years, but we're very appreciative of certainly the government sponsor support. The work that I'm mentioning here, these are the sponsors. We have several others as well, so I definitely want to make sure they're acknowledged. So that's it. Thank
you, Jamil. The paper is open for questions. We have 3 microphones, so please go use the microphones for questions.
Hi, Jamil.
Hey, Alex.
For the gravimetry time series testing, you had some times in gray that were banded out. What was happening then?
Let's go back to... Okay. So that is when we were at shore, and as we moved away from the shore. So these satellite maps, I mean, it's interesting. They're basically measuring to determine the gravity at sea. They're measuring the height of the ocean, and there's more error when you're at port. When you're closer, there's basically less water around. So when you're out at sea, your errors are smaller. So that's where the maps are less reliable. And so these things are banded because that's where you may expect that your error deviates from the maps because the maps are less good, basically, there. Any other questions?
I'm going to carry one around if anyone wants to ask a question and not go to the microphone.
Hi, Jamil. Great talk. So one kind of technical question. If you did your local G measurement differentially, I would imagine that you could subtract a lot of the big variation that you get from being on a rocking ship. Would it make the sensor bigger and less accurate? Or
one of the challenges, yeah. So we also do build gravity gradiometers. It's the scale of what you're measuring. If you're measuring gravity gradients, you're trying to measure gravity gradients of the seafloor. Those signals will be smaller because they fall off as r cubed versus r squared.
I see. So you don't win in the end.
Yeah. So you don't, and then you also need a map. And so the reason this works and the reason it works at sea is that you have this alternate way of building the maps, which is through this altimetry of, and then basically, some calculation of inferring what that local gravity must be. Right. The same technique wouldn't work over land. The question is always, well, great, you built this thing, where did the map come from? And it's this other modality that's used.
And then I guess a follow-up, if you were to combine the fact that your sensor is both an inertial sensor and a local G sensor at the same time, can you use both modalities and decrease in one mode that accuracy that integrates over time?
I think the challenge there is to discern real acceleration from what gravity is. That is part of the challenge. And so the sensor measures whatever it measures, and then there's some processing that has to happen because of that, because it's operating through this motion. And so in this picture that I've drawn, in this kind of little schematic that you see here, there really is a connection between the atomic sensor and the inertial sensor, where the inertial sensor is providing angles. It's providing, and that's allowing us to do this correction, basically, of the measurement to, in a sense, discern what is real, gravity, or what is a real gravity signal from just platform acceleration. That's the big challenge.
Okay, great. Impressive work. Thanks.
Thank you.
Similar along those lines with your accelerometer you mentioned, when you're on the water and it's nice and smooth, it's probably fine, but if you get a little choppy and that ship comes down hard, do you ever peg the accelerometer and have to reset it, or what kind of effect does that have on your measurements?
So that's exactly, you really, there's not going to be a silver bullet sensor that's going to solve all your problems, be highest performing, and allow you to operate under dynamics. We knew what the ship motion was going in, and we designed a sensor that basically wouldn't peg, like you're saying. You're absolutely right. That will happen at some point. You'll lose contrast in the system, or the atoms will move out of the measurement region. We designed in some margin, so we had some expectations, and when we operated on that smaller ship where I showed you the motion, the dynamics were worse, but we were still able to operate through that. But if you went, if you put it on a hypersonic, missile or something, yes, absolutely, it would rail, as all sensors would. But if we were to have designed a much more sensitive, device, which could measure below the levels that we needed to. It would peg, as you said, under pretty benign dynamics. So it's this trade-off. It's basically, kind of a sensitivity bandwidth product. We lower the sensitivity to up the bandwidth so that we can operate under real dynamics.
Yeah, thank you very much for very impressive work. So I'm curious about this time synchronization technique. Could you comment on the acquisition time? And also I was wondering if this would be suitable in the end for movable systems or even satellite to ground synchronization?
Yeah, those are all good questions. I would encourage you to check out some of the papers by NIST, but first things, these are some of the questions that you would have. These are natural questions. What you're asking is, how practical is this scheme? And one of the things is, does it require a lot of power? No. Basically the idea is you're exchanging optical pulses over free space, and then you're doing some local comparison of those optical pulses to pull out the synchronization. The acquisition time is less than a millisecond. You can get this over over about I think 500 microseconds to do this acquisition. Now, because you're doing this two-way transfer, and there are things like turbulence in the air, things like that, most of the time you're not receiving signal at the sensor. So every once in a while it basically flashes on, and you have that, and you're able to maintain that synchronization. Because the two things that are exchanging these pulses are highly coherent, they kind of operate as a flywheel, and they're good enough over that time. So the kind of quick summary answers are, it requires only a little bit of power, kind of picowatts, and if you're doing this over tens of kilometers at sea level, this wasn't done at sea level, this was done in Colorado at mile high, that's atmospherically equivalent to going from ground to a satellite. And so NIST recently, kind of with the hardware you're seeing here, demonstrated this over 300 kilometers. So certainly enough to go to LEO, and they basically, and same with us, kind of turned down their power to see that this is the equivalent power you would get even going up to GEO, to those levels. So in terms of the baseline, it is an acquisition time that's doable. The real challenge now is if you have a satellite and it's moving 7 kilometers a second with respect to the ground, there's big Doppler shifts that can confuse that measurement, and so that's what needs to be worked on now. So in a static, if it was truly static, geosynchronous, you would be likely able to do it. They're developing algorithms to deal with the Doppler shifts.
Mm-hmm. Hello, I have a question too. So following the previous question on synchronization, I presume some of the biggest challenges here to put this on a satellite and create sort of this global synchronization network is ruggedizing both the optical clocks and sort of, more importantly, almost the frequency comms.
Mm-hmm.
So can you comment on just what is the state of this, how far we are from having frequency comms that you can actually mount on a satellite and
sure,
put on a network?
That's a great question. These frequency comms have gone from large kind of rack mount, full rack devices now down to, I'll show you, I have a picture of ours here. Yeah, so this is the frequency comm, the optics package that we've built, which is roughly this size. The challenge is, if you're going to put something in space, is how is it going to handle things like radiation? How much power is it going to draw? Frequency comms are actually the big power draw in these clocks that we build. So that's something where there's a couple problems to attack with it, and so we have developed photonic integration, which allows us to reduce the power of this frequency comm down from typically like 20 watt scale down to 6 watts. The other issue is that they use some weird optical fibers, typically highly nonlinear fibers. and those can have problems with radiation potentially. And so again, if you can replace those fibers with things like silicon nitride, you know, other materials, lithium niobate, that we know are compatible with space, we can do that. And so we're working in that direction ourselves to replace what we see as the sensitive pieces. Much of the stuff is fine and it's flown. It's just a couple items in those combs that could be a problem. But I think that is addressable. And I would say in our current comb, it's, you know, everything is addressed, but maybe one piece, and we're hoping to address that next piece. Does that answer the question? Okay, great.
Any other questions? All right, with that, let's thank our speaker.
Thank you.
Yes, and thank you, Jamil, again for just a wonderful talk and the extra time answering these questions. We are now scheduled for a break. There's been a slight change in our program. Dr. Spencer Olson, who many of you know from our Space Vehicles Directorate in Albuquerque, long ways away from here, he ended up with now 1 but 2 flight cancellations, so Spencer can't be with us this morning. We're hoping to get him here later in the week. We'll see if that works out. So what we're going to do, we're going to take our scheduled 20-minute break now. We'll reconvene at about 10:45 or so, and we'll give some extra time to our remaining 3 speakers for this morning. So thank you very much for a great opening session. Great, thank you very much, Jim, and hopefully everyone had a great break and was able to network and meet some new folks. As we said, that's all one of the biggest benefits of Q4i. So next, we're very privileged to have Professor Cass Sackett, an associate professor of physics at the University of Virginia. Dr. Sackett's groundbreaking experiments studying the quantum behavior of ultra-cold atoms, particularly in trapped Bose-Einstein condensates, have paved the way for advances in precision navigation, gravimetry, and fundamental physics. Welcome, Professor Sackett.
Thank you very much. It's a pleasure to be here. It's my first time at this workshop, but it seems very exciting, and I'm happy to be part of it. Right, so I'll say a little bit about quantum sensing, the area that I mostly focus on. I actually debated a little bit about what would be most useful for this audience, so I hope I came up with something that's good. I'll tell you a little bit about kind of my picture of what quantum sensing really means and the sort of areas it involves, and then just a couple of the things I've been working on with this rotation sensing, and then I'm involved in this NASA project on the space station, which is a nice example of getting some of these kinds of techniques into the field. So I'll say a bit about that as well. Maybe. So the big picture, right? I mean, it's nice as a physicist. It's very exciting that we're getting rather good now at implementing quantum technology. That's sort of physicist stock and trade for quite a long time. What do we mean by quantum technology? Well, different people mean different things. I think, you know, there's a sort of, if you look it up on Google, you'll get some kind of BS picture like this. Of course, the things in real life look more like, you know, things on the bottom here. I feel like it's a little confusing because they're sort of different areas. I mean, broadly speaking, quantum technology would be anything to do with the quantum nature of matter, which includes, you know, LEDs and even fluorescent lights. I mean, we've been doing quantum things for quite a long time, in fact, transistors, for instance. But I think more narrowly, people usually think applications that really rely specifically on quantum superposition and or entanglement. And that's more of the new kind of thing that I kind of tend to think about. Examples of that, of course, lasers are probably the first quantum technology in that sense that you might say. MRI machines, like I have a picture of here. Magnetometers, gravimeters, optical clocks. And of course, things that are coming up more in the future, those things all exist, coming up in the future, quantum computers, cryptography, gyroscopes, and inertial navigation, lots of things like this. And then, of course, from my background in academia, I mean, there's an enormous range of scientific experiments that we don't really need full-on technologies for, but they're certainly advancing our understanding of the universe, so that's important too. So that's a range of things that have existed for a while, things that are upcoming. It's an exciting time. In terms of more narrowly to quantum sensors, so this is applying these ideas to trying to measure something better than you can do without quantum mechanics, of course. A lot of those, not everything, but a lot of it relies on using individual atoms or ions. There's a good reason for that, is that isolated atoms are just a very nice stable platform in a lot of ways. They're very reproducible. Every atom's the same. Every atom's the same today as it was yesterday and will be tomorrow, up to very tiny effects maybe. And so they make a very good reference. If you want to measure something in a nice, repeatable, standardized way, using an atomic reference is the way to go. Now, unfortunately, the drawback to that is that if you're using isolated, even a collection of distant, well-separated atoms, there's rather poor signal noise. You just don't have a lot of matter there to interact with, and so you don't have very good signal noise. So it means it's stable, but you don't have a lot of sensitivity in the short term. Usually, you deal with that by hooking it up to a more classical type of sensor, the archetype being an atomic clock, where you're using the atoms as a stable reference. But you've also got something like a maser or a laser there that provides good short-term stability and a high signal to noise, and you have to make those operate together. And I expect that modality is going to carry on to other types of quantum sensing as well. And of course, the advantage of that is by putting them together, you get sort of orders of magnitudes improvements over what really either one could do by themselves. So I think it's important to realize that no quantum sensor is probably going to be operating in isolation. In most of the things, I think they're going to be working together with more conventional systems that need to be very good too. So it's not like the end of classical physics or anything. Some of the areas of technology, actually Jamil touched on as well. Atomic clocks, of course, are the archetype of the field. They're well established and already do better than anything else. There's no real competition for measuring time compared to atomic clocks, and they're only getting better. Other ones are a little more upcoming. A magnetic sensor is also well established. You could argue, I would say, a squid is a perfectly reasonable example of a quantum technology as well. It works very, very well it's the sort of the gold standard for measuring magnetic fields now. Of course, the downside is everything has to be cooled to cryogenic temperatures. That's a big difficulty for applications. The atomic systems, though, are getting to be almost, I think, if it's not as good as squids now. And they work at room temperature, kind of comparable performance. Here's a kind of an example system that people that NIST are working on with this sort of chip scale magnetometers, and they're getting very, very good too. And I think the advantage of working at room temperature is just really huge. I expect for most sensing applications that's what you're going to want. Electric field sensors also coming up. These use Rydberg atoms. And Jamil noted this too, that you can actually be much, much better than an antenna in the right circumstances, and so there's a lot of interest in that. The thing I particularly mostly work on is atom interferometry, so I'll describe that in a little more detail. The big applications there are measuring gravity, like Jamil talked about, but also accelerations and rotations, other things as well. But those are the main ones, and they of course have applications to inertial navigation is important, and also geophysics. So atom interferometry, just say a little bit about what that is if you're not familiar with it. So the basic concept is to take an atom, which has a quantum wave function that says where it is and how fast it's moving, and to use physics tricks to establish it in a superposition of two different states. So to basically have some amplitude, some probability it's in one place, and some probability be in another place that are spatially separated. That's the sort of core thing. Once you've established that, you let them interact with the environment. The two branches of the wave function pick up different phases. They're actually, if you've taken any quantum at all, this is kind of familiar. It's just the Bohr evolution of the wave function. So if the two locations experience a different interaction energy with their environment, you'll build up a differential phase. And then you bring them back together somehow. You separate them out, you bring them back together, and they interfere, and the phase of that interference is set by that differential phase that developed. And so by measuring it with maybe a picture like this, you can read out what that phase is and learn about your environment in a very, very sensitive way. Basically, the fact that we get divide by Planck's constant here is very small. which means we can measure very, very small changes in the energy, and so we're very sensitive to the environment. So, like Jamil pointed out, there's many lab-based successes. I mean, if you just look at sort of the best you can do in a lab, the atom interferometry holds a lot of records now. It's the best measurements of gravity, basically tied for the best kind of measurements of rotations. They measure recoil velocity is important for physics. We get the fine structure constant very accurately from that. That's pretty interesting. People are using these to test for dark matter and beyond standard model physics. A lot of not super important application things, but they're interesting to lots of people. I'm not being fair to Jamil here. I said at one point there was really one sort of commercial atom interferometer product that you could just go and buy, and I think that's the X-Blue gravimeter now. My understanding is that's basically the best absolute gravimeter you can buy. It's essentially as good as the classic falling corner cube ones, and in some ways more convenient to use. It's a sort of a big, this is kind of a lab-in-the-box system like Jamil was talking about, so it's not exactly part of an inertial navigation system, but it's a very good gravimeter. So a big effort that a lot of people are undergoing is sort of to transition these technologies, like Jamil's doing, from the lab to platforms that are more applicable, that can go out in the field, that can work in a more practical way, because that's what we want to use them for. So a lot of people, this is focusing on my kind of thing a little bit, the sort of standard garden variety, as such as it is, interferometer typically uses atoms in free fall, so that they're not being held by any sort of external fields or anything. You know, that's how you measure gravity. If you want to measure gravity, they basically have to be in free fall. And to measure gravity really accuracy, you end up with like these big giant towers, so you can really drop the atoms a long ways. If you do that, you can measure gravity with phenomenal precision, but it's sort of not very useful for most of the applications we think about, because you can't put big giant things on a boat or an airplane or a car. So for most other sensing modalities, actually falling is just pretty inconvenient altogether. If you want to measure horizontal acceleration, having them falling vertically is just a pain in the butt. The solution I and other people work on exploring is to kind of keep the atoms confined in some kind of trap, to hold them against gravity, keep them from spreading out, so they just do only what you want to do. So that's a little bit more niche. There's different ways to do it, though. So I use magnetic fields. I might say a little bit about that. You can also use lasers to trap them. So there's various ways to do this. I think a very nice way to think about this is an analog between like a free space laser interferometer that you might have built in like an undergraduate lab or something, and a fiber interferometer, which is what applications mostly use. You put the laser in the optical fiber. Now you don't need all these mirrors and big space, and you can't interrupt the beam. It's just much more convenient for applications in many ways. But the cost you pay, that you have to be prepared to pay, is that the trap's never going to be perfectly stable. And so if we're holding atoms with magnetic or optical fields, they'll be a little bit noisy. That's always going to introduce some noise and some imprecision. So the goal is to try to trade off in a successful way some of the performance, some of the absolute sensitivity, stability that you can get in free space, with a more applicable, usable system that's still good enough to be useful. And there's reason to do that, because the lab-based systems are actually really quite amazingly good. So they're really much better than they need to be for a lot of applications. I think it's interesting, you make the same trade-off. You make an optical fiber interferometer, you also lose stability if you want the very best. This is a little bit why ring laser gyros tend to be better than optical gyros, is because free space beam, put them in a fiber and you pick up sources of noise. It's just in many cases the convenience of that makes the trade-off worthwhile. I guess this is just a little picture of the typical technology we use. So this is an atom chip. I'll show you one of ours too. It's a bunch of patterned wires on a substrate of some kind. You put the atoms right up next to it, sort of centimeter scale. It's 3 centimeters across. And so with that technology, you can imagine making sort of a sensor whose active element is on the centimeter scale. And with photonic integration, you don't have to add that much more volume for getting lasers and things like that either. So I wanted to explain a little bit. I don't want to have it be totally magic, how you say like, oh, well, I'll just make a superposition of atoms in different places. That sounds straightforward. So I'll say a little just about how that works. The sort of leading technique is Bragg or Raman splitting, but using a laser beam to do this. So So this is like basically the atom optics analog of a mirror or a beam splitter. And the idea is you start with an atomic wave function here, say, and we apply a laser beam that's running, maybe you send the laser beam in and bounce it off a mirror, so you have two beams coming from both directions. That makes a standing wave. And you can kind of think about that if the atom started at rest with this momentum zero state. You take this laser, you've detuned it from any of the strong atomic resonances, maybe not by too far. So you can't just absorb a photon. It's off resonant for that. But you can absorb a photon, say, from this beam and go up to sort of a virtual state, sort of an off-resonant excitation. You just can't stay up there very long, and so you can be driven back down maybe by this beam. So if you absorb a photon from here, you actually pick up an h bar k momentum kick from that photon. And then if this beam comes along and stimulates you to emit a photon to come back down, well, you recoil and you get another 2 h bar k kick in that direction. So basically you've driven sort of like a Raman transition, you might think, from a ground state to a virtual excited state back to a ground state, but with a different momentum in the end, and that gives you a kick. And the reason this is kind of the way we do it, at least we have this all symmetric, so it's the same way going the other direction. You could absorb the other beam first, and so you can start with 0 and go up here. And so what we tend to see is we apply this laser beam, and then our little atom cloud splits very accurately into two-wave packets that move apart at about 1 centimeter per second in our case. So formally, the way you'd write that, you'd say the 0 momentum states gets put in a superposition of +2 h bar k and -2 h bar k, and that's sort of the starting state of our interferometer. I won't say too much more about that, but I thought it'd be useful to orient you. So let me go into this one application of rotation sensing that we work on. So if any interferometer encloses an area, so something where the two packets move maybe around a circle, it picks up sensitivity to rotation through the Sagnac effect. If you're not familiar with that, the idea is that if you're rotating this way, then the path that's kind of going with the rotation has to go a little further. The counter-rotating path goes a little less far, so there's a path length difference that gives you a phase shift that way. And it turns out, kind of amazingly, that the phase that you get is very independent of a lot of different things. For atoms, it's the mass of the atom divided by h bar again, the rotation rate, and the area enclosed. It doesn't matter what the shape of the area is or how fast the atoms are moving. You just get that phase. This works for atoms in this form. A similar equation works for light or sound waves. That's actually the basis for basically all non-mechanical, if it's not an actual physical rotating gyroscope. That's pretty much how all rotation sensors work, even the MEMS ones that are like our standard in a lot of applications now. The advantage of atoms is that compared to, say, light or sound waves, they move very slow for a given wavelength. And so when they're going around this ring, they're moving slow enough that there's just a lot of time for the system to rotate, so you have a bigger path length difference, and so you're more sensitive to rotations for the same area compared to other techniques. So like I said, you can do this with free-falling atoms, and the best performance you will expect, and indeed has been observed with atoms in free fall. But we don't want to do that. What we do is we put our atoms in a trap. We use a magnetic trap that provides like a harmonic oscillator potential. So just like a mass on a spring here, it's like a mass on a 2D spring. So there's some frequency the atoms would oscillate back and forth, and it's in 2 dimensions and kind of symmetric. So if you just kick them, they'd oscillate back and forth, kind of like a pendulum. What we do then is we prepare our atoms, a Bose condensate in our case, in the center of the trap. We kick them with our laser beam so they go off to the side. I'll play that again in a minute. And actually, so like I said, if you just kick them, they'd oscillate back and forth. But we don't let them do that. Let's see if I can. So once they get to the side, they're stopped. They're just about ready to turn around. We shine another laser beam on and do this splitting technique. And then that's actually just exactly the right speed to give them, the right momentum tip to have them run around the circle, just like the old things you used to have in restaurants where you put a quarter in that big yellow funnel and it would spin around, just kind of riding on the rim. So it's kind of like that. There's no forces keeping them in a circle. It's just dynamically what they want to do. So they orbit. Like you saw, the atoms are dilute enough that the packets can just pass right through each other with sort of negligible interactions or collisions. So they go all the way around, and then we apply that laser beam again, and the effect of that is kind of to close the interferometer. In the end, what you end up with is some of the atoms get brought back to rest and then fall back to the middle. Others are not brought back to rest and keep moving around. And basically the fraction of atoms brought back to rest is how we read out the phase. That goes like the cosine squared of the Sagnac phase we're trying to measure. Now it's a little more complicated what we actually do, because we started with atoms in the center of the trap and then we kicked them with the laser. That means we actually kick them in both directions because everything's symmetric. But that's actually great. It makes the picture a little more complicated, but actually what we really have is 2 interferometers. So we'd split them. Some atoms went over here, some atoms went over here. This is like a millimeter across, so we have one big beam, splits all the atoms together with the same phases. And then they go around in their own separate ways, and basically we do 2 interferometers at the same time. We really like that because any one interferometer is sensitive to a lot of things. There's many, many sources of noise, vibrations, laser noise, all kinds of magnetic field noise can happen. But by doing 2 of them in the same trap at the same time, most of those noise effects are common mode. They're the same for both since they're in the same environment. But because they're sort of on opposite sides going around the opposite ways, the Sagnac, the rotation phase, is differential. It's opposite for the 2. So by comparing the phase difference between these 2 interferometers, we can get the rotation effect without having to worry about stabilizing a ton of other noise sources, which is challenging to do in practice. So here's a picture of a sort of movie we put together of actual atoms doing this. So this is what it actually looks like in the lab. So the little dots are pictures we take, and here we've interrupted the sequence every time to take a little picture and show what you see. And so you could sort of see the 2 interferometers tapping the atoms, going around, passing through each other, and then normally then we'd let that all happen in the dark and just take this one picture at the end. And pictures are maybe not the best long-term way to do this data analysis, but for now we just measure how many atoms are in the middle compared to the sides, and that tells us what the phase was. So here's some of the specs that we have. We do this with a relatively small samples, a couple 10,000 atoms. On the downside, that makes it, our signal and noise is a little bit worse, but on the upside, that means we don't have to worry about them interacting with each other and colliding so much. It's kind of a trade-off again. The best we've done, this picture here was actually the nicest video we have, but it's a little bit smaller interferometer. We can actually get the orbit duration up to about 1/3 of a second, so very physical sort of time scale, with a diameter of like 1 millimeter, which is really big if you're thinking about atoms. But really small if you're thinking about the active area of a sensor, right? That's actually something that you could do sort of chip scale in a small package. So far we've been able to get the atoms to actually go around 2 orbits. That doubles the area. It gets hard to keep them aligned past that, but we can get up to 2. A downside for now, we can only run about once every 100 seconds because the whole experiment's rather slow, but that's a thing I'll say something about. But if you take those numbers, so it's a relatively large area as such things go, the Sagnac phase we get, the sort of the sensitivity to rotations is tens of thousands of radians per radian per second, if you like. And I'll talk about this, if we could measure this at sort of shot noise level precision, so basically limited only by the physics as well as far as measuring how many atoms are in each of those packets, we could get down to a phase sensitivity of about 0.01 radians, which would be a rotation sensitivity of like 250 nanoradians per second, which again is not the best. The best is like 1 nanoradian per second. But it's quite good enough to be interesting for a lot of navigation purposes. So if you could really, I believe that if you could take that performance and put it in a reasonable, cost efficient and low volume package, people would be very interested in it. So we're hopeful that this is a nice track. Now, unfortunately, we're not shot noise limited. In fact, this is sort of our current bête noire. The noise is worse than we thought. We can run this, so it's good enough we can run it for a long time. So we did a big 30-hour data run. It does take some babysitting, so this is a bit hard on the students. But and we do observe phase noise. Actually, you can kind of see this is the way we can analyze the data. So each of these points is one run of the experiment. This is one of the 2 interferometers, and the horizontal axis is the other one. If you just plot those against each other, we want to extract the phase difference. But each individual one is noisy, so it's not like we can totally just measure and then subtract, because if you're on a fringe, you don't know exactly where you are. So what we do is plot them versus the other, and if everything is perfect, they would fall on an ellipse in general. So here it's almost a circle, but it could be, if they were perfectly correlated, if the phase difference was 0, they'd be on a line, right? They would always agree with each other, so they'd be on a line. So we can plot that and fit it to an ellipse and get the phase, so we see what the phase, I don't have it written down. But it does look pretty noisy, like those points are not very well lying on the circle. And that's because it actually is. So we can do this, and we can divide it up into little chunks and make an Allen deviation plot. And you can see on the one hand, so this line is going down like 1 over square root of t, so it's averaging down nicely. That's one of the promises of atoms, using atoms, is that they should be very stable and integrate down for long times. But the intercept is kind of terrible. If you back it out to the noise per one run, we can't exactly get a measurement for one run, but if we just extrapolate backwards, it's 0.7 radians, right? So it's like 40 degrees. So that's a much, much worse than shot noise. Which isn't completely shocking. Like I said, you're going to trade off. If you put these things in a trap, you're going to introduce some sources of noise. We shouldn't be this much. So this is the thing we're kind of working on right now. We think that our trapping fields are noisier than we were hoping, and rather noisier than they need to be. And so we're basically building some better, actually we've got them built now, we've got some better current drivers. They're just electromagnets, so we just need very clean, stable currents. It's just an electrical engineering problem, so we're going to put those in, and hopefully that will improve substantially. So we'll see how that goes. But this basically is why this is still in a physics lab, as there's obviously some things still to be working out here. But we do think, people have gotten shot noise limited atom interferometers before. We hope that we can get at least close to that. So here's what this apparatus looks like. This is in my lab in the basement of our physics building. So it's an optics table with a bunch of mirrors and cables and all kinds of things. So it's far away from something you want to put, in any kind of application. Here's a little zoom in. Actually, this is the business end of it. This is where the middle of that chamber is where the interferometer actually takes place. That's a 6-inch vacuum flange. But we're also working on making this more compact. It's not really to the level that you'd want for an application, but we're not ready for that yet. But we do have this system where basically at least the vacuum and the optical components and things are on this sort of breadboard system that's like 1.5 feet by 1.5 feet and a foot. So much, much smaller than a big table. My student uses a banana for a scale. I thought that was a pretty good idea. So it has all these little small mirrors. There's a small vacuum cell that goes in here. This kind of integration. It's not, again, the end goal, but it's a step in the direction of something that's better. We particularly wanted this ourselves so that we could move this somewhere and put it like on a shake table or a rotation table and actually do some more environmental testing that we can't do with a full optics table. Part of this is that we have this atom chip. This actually was built for us by the AFRL folks in Albuquerque, which was super helpful. It's kind of pretty basic. These sort of circular things are actually just spirals of wire. They're just electromagnets, so these are just basically coils on a chip, but it makes them small. We can put the atoms right up next to it, so we can get really strong fields, and having it on a chip just makes everything stable and more compact. And so we're excited to use this. We haven't implemented this yet, but that's sort of next on our list, is to make this happen. So for this part of it, I think it has pretty nice prospects. It's still research in progress, but I think there's a lot of promise to achieve high, not the highest, but interestingly high sensitivity. We need to see if low noise is achievable, and then once we have that, we really need to look at long-term stability. I mean, we have some evidence that it's not terrible, but it does need to integrate down over long times if this is going to be useful. But because they're using atoms and we're designing things well to not be too sensitive to like temperature and things like that, it should be pretty good. There's good prospects for reducing size, weight, and power. We have a sort of a system that's getting in that direction, and then the next generation, of course, would be to take advantage of photonic integrated circuits. So, I mean, even in this new compact system, we still have big laser systems, but there's a lot of work involved in people are doing to sort of integrate the lasers and the optics right into the package, and that's going to be a real game changer, and that's making good progress too. But I'll iterate again. You can poke a lot of holes in this if you thought that this was going to be the only thing that was going to let you navigate. Like, for instance, in the best case, this is still going to run only once every few seconds or something in this model, and that's unusable for navigation. But my picture is always that you'll have this hooked up to a more classical system that updates more quickly, and really the goal of this is not so much to tell you what your rotation is, but to sort of stabilize the drifts of like a fiber gyro or a ring laser gyro. and it needs to be good enough for that. And I think there's it should be. I think it's very reasonable that it could be. So that's that part of it. I wanted to say a little bit about this other project we do with cold atoms in space, because I think it's kind of applicable too. It's something you should know about. So space station is fun to look at. On the space station is the Cold Atom Lab that was constructed by JPL and launched actually up in 2018. So it's been there about 5 years, and it's been running that whole time. Actually, this is it's completely remote. The astronauts are there, but they don't babysit it in any way. They run it actually. Operators sit in JPL. They just run it over the space internet, just like my students in lab run things from their computer. It's got both rubidium and potassium atoms. It runs. They get about actually 100 to 200, I guess, depends, a good or a bad day, of sort of science runs for several different science groups. I'm one of about 5 right now. There's experiments on a bunch of different things. I focus on these microgravity cooling methods. People are looking at bubble-shaped BECs. That's an interesting physics problem. FMOV state is a many-body physics problem with interesting quantum effects. And also atom interferometry. Actually, that's a big thing. A big goal of it. Everyone at NASA understands that there's a lot of that atom interferometry is an important quantum sensing modality, and they want to support that in space. So the way that works is not fundamentally different from what we do in my experiment on the ground. There's a vacuum cell here that we can collect the cold atoms in. There's a little hole there's an atom chip on top, same kind of similar atom chips like I talked about. There's a small window in it. We can send a laser beam through. This is the one that does the atom interferometry Bragg splitting. It's a first step. It's not designed to be high performance. It again, like my own experiments, has pretty low atom number. There's no vibration stabilization at all, so that limits the things you can do. The Bragg beam quality is came out a little bit worse than we were hoping. They're doing an upgrade to help improve that, so we can get some better performance. But it does let you do a bunch of demonstrations. So we've demonstrated just that you can do atom interferometry, and I thought I'd just flash up the work that we did on a recoil frequency measurement, just because it's in space and shows you that you can do things remotely in a fairly compact system without, it's a road to a field application. The Ramsey interferometer itself, just a little bit about the physics, I won't spend too long on it. It's a very simple 2-pulse interferometer. The idea here is if you map sort of position like X versus T, if the atoms were just sitting here, they'd just be moving at some velocity. We launched them out of the trap at some velocity. These are in free space. I should mention, like my whole thing on the ground is to use atoms that are in a trap so you don't have to deal with them falling. The other solution to that is to be in space where nothing falls, and so that's great for us. So you launch them out of the trap, they're just moving. At some point we give them a Bragg kick. We can do this in an asymmetric way where we just kick one of them, they get a 2 h/k pulse. A little bit later we straighten that back out again, so they're moving at the same velocity. This kind of big smear out is like the size of the wave function of the Bose condensate we're using. Where that's overlapped, that purple area, you see interference. So you can't let them get too far apart or they don't interfere, but we just look in that region where they do. In this case, the phase is not from gravity or rotations or anything like that. It's actually, in this case, from the different kinetic energy. These atoms here are moving faster than the other ones, and so they have a different kinetic energy, and you get a phase from that. We measure that here. This is the difference in kinetic energies. Works out to be this thing we call the recoil frequency, is a characteristic of the K's 2 pi over lambda. It's a characteristic of the laser you're doing to do the splitting. On the ground, this is a big important thing. This is how you get the fine structure constant accurately. We're not trying to do that, but in space, this is mostly just a demonstration, but on the ground we have sophisticated tools to measure exactly what the wavelength or the frequency of the light is. The space station doesn't have that, so this actually is a way to check and make sure your laser wavelength hasn't changed or measure what it is. So we do the experiment that you can do these asymmetric pulses if they're moving originally. If the initial momentum is not 0, then you can choose your laser detuning to either drive to P plus to h/k or minus. You can control that. And then we do these 2 pulses and we vary the phase of the final pulse, and you actually do get this nice little sinusoid. We can fit that. Here's a picture of what it looks like. We have, ideally, it would just be these 2 states. There's a little bit of population in the third state because the pulses aren't quite perfect. We fit that to a sinusoid with an offset phase and basically just plot that phase as a function of time for both the 2h bar k and the minus 2h bar k fits, and the slopes of those lines tell you what that kinetic energy difference is. And from that, actually, you can back out both the recoil frequency and the initial velocity is not fundamentally important, but you need to know what it is too. So we do that, and we have this embarrassingly imprecise recoil frequency measurement. People who do this on the ground get like 9 digits or something. In space, you'd want to do a little better than this, but still, I think it's the first measurement of a physical quantity using atom interferometry in space. So I'm excited to have done it. And it's consistent, so we didn't get the wrong answer. That's good. And it is a very precise measure of the initial velocity if somehow you do care about that. So, this is a demonstration. There weren't any obvious problems. The next steps are to, like we said, the Bragg beam's not so great. We want to improve that so we can do longer time interferometry. So far, it's only about 10 milliseconds, which is sort of trivial to do on the ground. So the motivation to go into space is to do longer times. The prospects, though, I mean, it is a technology pathfinder, and I think it found the path. Shows us how to work with cold atoms in space and identify problems. There were many interesting problems that have come up with this. Future efforts are going to be more focused on higher performance and new physics. A big scientific question is the equivalence principle. Do potassium and rubidium atoms actually both fall, i.e. orbit at the same speed, or is there a slight difference? Inertial navigation techniques, developing those are very, very important to NASA. Navigation in space is not so easy. A good inertial navigation system would be useful. There's, like I said, other microgravity phenomena. The plan, I think, is for Cal itself on the space station to orbit, to operate for the next few years, 2026. And then it's going to be replaced by an even nicer instrument called BCAL, which is kind of a funny name. It's a much more elaborate system being put together by the German group in collaboration with their space agency. And that's going to let us do a whole bunch of different experiments, both on the physics side and the application side. So we're all excited about that. Okay, so I'll try to wrap up. So I want to say quantum sensing is demonstrably already a very important technology for all of us. I mean, GPS is a good example. Atom interferometry specifically is sort of in the midst, I hope, of moving from a research topic to a real tool for applications. My business with rotation sensing, I think our technique has some promise. It's got good performance, and there's I think a pretty clear path to something that's interesting in terms of performance and swap and simplicity. And then the cold atom lab, I think it just really demonstrates that you can get reliable, long-time operation in a remote environment without babysitting for a long time. It's still kind of a lab-in-the-box type system, but it does work well. And in the long term, it's a challenging environment, but it does work. And so there's a future for cold atoms in space as well, and I think it says something good about cold atoms on the ground too. Right, so a bunch of people work with this. I've got students in my own lab and former students, and then lots of collaborators at lots of different places. Actually, I should have put down my collaborators at AFRL too. It was mostly Brian Kasich and actually Spencer Olson, who couldn't make it, and Matt Squires are the people who run the things over there. And thank you for your attention. Be happy to take some questions.
What are the physical systems where you use the rotation sensing for?
Gosh, could you move a little closer to the mic? I couldn't quite hear.
What are the physical systems or situations where you would use the rotation sensing for?
Sure, there's a few. And it's a complicated question because it depends exactly what your rotation sensor can do, and ours can't do that much yet. But the vision, I'll tell you where I think atom interferometry rotation sensors are particularly likely to be useful. Are again, the hope and advantage would be the low long-term drift. So long missions like on a submarine, like these 30-day things where you want to do navigation for a long time, where you could have a rotation sensor there that keeps your optical gyros from drifting too much. That you need that and good accelerometers as well. So that's one. So long duration missions. Submarines is one example. Spacecraft is another. I mean, atom interferometry is just a really good fit for space because you don't have this gravity problem, and it's an important problem that inertial navigation in space is really kind of would be very, very useful for missions to distant astronomical objects, to avoid getting lost or needing to fire your engines more often than normal. And then the other example I know about is actually north finding. If you have a good, I like this for atom interferometry because north finding would be just what direction is north, right? Magnetic company is only so good. But if you have a good 3-axis rotation sensor, you could just run it and get the vector rotation, get the rotation vector, and that's by definition north. And a nice thing about that is that it's in some situations okay to do that while you're sitting still. So if we are plagued forever by problems of sensitivity to jostling and accelerations, and we never can make those really work as well as we want, at least there's an application where you don't have to be moving to have it be useful. So I think that could be a nice example too.
Hi, Cass. First of all, congratulations putting anything in space. That's
thanks so much. Actually, again, your microphone is either not working or you're not.
Okay. Maybe I can just be very loud.
I can hear you, but I don't know if everyone else can.
Okay. So maybe a kind of fundamental science question. Sagnac interferometers are great, and they're really sensitive to non-reciprocal types of effects. So obviously rotation being king among them.
Right.
But you happen to use BECs.
Yes.
And, we know that single atoms don't have a lot of other non-reciprocal effects other than like spin-orbit interactions. But with the BEC, is there some level of sensitivity at which you might start to see kind of interaction-driven non-reciprocal effects?
Oh, absolutely, yes. In fact, it's a whole thing. It's a spec called phase diffusion. I like this topic a lot, so I might give you a more detailed answer than you want. The issue is if you're using condensate, which there's another question of why we need to use condensates, but condensates are so cold and the atoms are relatively close together, they do interact a little bit, not very much. It's a very weak effect, but it is there, which means that these little packets, like the packets you saw moving around, the energy of those packets depend not only on rotation in the trap and everything else, but how many atoms are in the packet. Because if there's more atoms, there's more interaction energy, and that also contributes to the phase. The issue is that after you've done this splitting, each individual atom's in a superposition of one or the other, so you can't actually say, and in fact it's not physically well defined, how many atoms are in that packet. Like there's a quantum uncertainty in the number of atoms in a packet. This is the same thing with the number of photons in the arm of an interferometer. That means the interaction energy is quantum uncertain, and over a long enough time the uncertain phase from that builds up and washes out your interference effect. Fortunately, well, you have to be aware of that problem. It means you're going to have trouble if you're trying to do a lot of atoms in a very tight trap where the density is high. In our conditions, in our, by design a little bit, for our number of atoms in our trap, we have this really weak trap. It's a very small effect. It comes in at like 10 seconds. So if you were trying to do like a multiple minute interferometer, you'd have to worry a lot about that, but that's not a direction I see going. So.
And then maybe a related follow-up question. I think that you mentioned that you have something like 10 to the 4 atoms in the BECs that are in the interferometer. What is the angular momentum that you work at? How many units?
Like how many H-bar?
Yeah.
I calculated that once, and I can't say I remember the number. It's enormous, though. It's like, I mean, it's macroscopic number, like 10 to 12 or something like that. Yeah.
Is it bigger or smaller than 10,000?
Then what?
Than the 10,000 atoms that you have.
Oh, it's many /k per atom. So.
Okay.
Yeah,
right,
yeah,
so
yeah. It's
so
not.
larger.
You're not in the vortex regime at all. It's thousands of H/k per atom, like
Okay.
millions, I think, even.
Great. Okay. Thank you.
Sure.
All right, let us thank our speaker once again. We'll catch up on Monday.
I will be around. So.
Thank you very much.
Thank you.
All right, thank you once again, Professor Sackett. Our next speaker is Dr. Noel Goddard, the CEO of Qunnect. Dr. Goddard's visionary leadership in the development of first-in-class hardware for quantum-secure networks has revolutionized the existing telecom infrastructure. With a rich background in physics and entrepreneurship, Dr. Goddard has made significant contributions to the fields of quantum technology and life sciences. Here at AFRL, we've worked with Dr. Goddard and Noel for several years and been very pleased with where the research is going and in terms of the products that have come of it. With that, Noel.
Hello. Hello, it's great to be here. It's actually really exciting to be here and to see how much the venue of Innovare has changed over the time of it starting as a vision and now becoming a reality. So always a pleasure to come back and to see how it evolves. So I'm going to talk to you today about a slightly different topic. We've heard both speakers proceeding on sensing. However, we also use atoms, so there will be a common theme here. However, we use them for quantum networking. And the title of the talk, The Practical Distribution of Useful Entanglement, is very specific because I think something which ties in the theme of both the first speaker and the more recent speaker is that as we are seeing quantum evolve and as we're seeing it go towards something more commercial, we also have to think a lot about what's good in the lab, what's good when we talk about field deployment, what's good when we're starting to talk about commercial use cases. And Qunnect definitely is in the space because of networking, of being more in the commercial use case space. But it all starts with trying to do things which go out of the lab to being field deployable, et cetera. So let's dissect the sentence for a moment as the exercise. So when we say practical distribution, what we're talking about is instrumentation which actually is designed to take stuff out of the lab, put it into the field, hopefully address it remotely, and to do so on existing infrastructure. Why this is interesting is, of course, quantum doesn't particularly love telecom. There are not all that many systems that work natively at telecom, but we have a huge amount of telecom fiber deployed across the US and globally, of course, which could be utilized for quantum networking if we can get over that barrier, right? When I say useful entanglement, I think something which we're also learning a lot about as we're seeing more technologies cross into the commercial realm is that the types of qubits that we choose to work with have to be qubits which allow us to scale to applications other than simply communications. There's, of course, a sort of rich body of work in the last 10 years of using all sorts of types of qubits to do communications. Probably the favorite of all of those is time-bend qubits. While those are good, they're also not native to physical systems. So if you'd like to use them for something like interfacing atomic sensors or interfacing atomic computers, you have a problem that you need to have a compatible qubit. And that's something that we take very seriously at Qunnect, and I'll speak a little bit about that as we get into the slides. And then finally, this idea of what good is networking if it's constrained to short distances. We all have to start somewhere. We know that technology evolves. So I would say that right now you're definitely looking at the earlier versions of what quantum networking means. But if we want to actually build a system, we should be thinking about how can that system actually be compatible with the next generation system, which can extend its use. And in this case, I think everybody in the room is probably familiar with the term quantum repeater. That's actually what Qunnect started off doing, is we were building a quantum repeater product suite. But as we started thinking about the products we were building, we were thinking a lot about how do we go step by step in a system which continues to be compatible with the other quantum technologies which are being commercialized around us. So I'm going to speak a little bit about the evolution of quantum networking. Everybody here is familiar, obviously, with digital communications, which the basis of that is basically that you carry information in bursts or pulses of light. Those have a mathematical encryption, which allows you to, again, store data, which you can then decrypt later. And the application which we use today for everything from streaming Netflix and doing financial transactions is secure communication. The promise of quantum communication is to up the ante, and instead of doing things which are mathematically encrypted, which have this sort of existential threat of being broken by quantum computers, we now physically encrypt our information within the particles of light themselves, so the photons. Unlike the atoms we were talking about in the last talk, which you actually want to interact, one of the great things about photons is they don't interact well, so they're very good for carrying information. And when I say physically encrypt, you pick some state of the photon in which you can use as your sort of information bit. The application of this, of course, is ultra-secure communication. And I think the promise that we all hope for, and something which has been driven home by the agenda of the National Quantum Initiative, particularly as seen through the Department of Energy, is that this will evolve into something which will be a big vision of not only just quantum communications, but something that looks very analogous to the internet we have today, which they call a quantum internet. So what is a quantum internet? It is a series of devices which are quantum connected by quantum channels. That's, of course, a very long-term vision, but it is the promise of what we hope we can do in order to do things like distributed sensing and computing. So there's some technology which exists today. First and foremost, the first generation of communications equipment would be in that central category, so quantum communications on physically encrypted particles. ID Quantique is basically the eldest company in the batch producing these things, which is Swiss. They have a new facility now also in Austria. And Toshiba, which has a basic research lab in Cambridge, England, and has been also producing a number of very high standard QKD devices. So we are going to call that hardware QKD hardware, so quantum key distribution, which has unfortunately gotten a bit of a black eye with the Department of Defense because the United States does not think about using quantum key distribution as a sort of evolution of quantum networking. The NSA was concerned and put out a public statement about how they don't see that at its current state that all industries should be upgrading their equipment to QKD equipment because there are some fundamental flaws in QKD. However, I think what QKD teaches all of us is that you can actually communicate with single photons. It's a very important thing, and of course it's not something that's just trivial to do on existing infrastructure. Europe has decided that they are going to do QKD as a path to quantum internet. The US has some different efforts, right? But in the Department of Defense, they've thought a lot about the idea of how does quantum augment existing digital networks. And in the DOE side, they've gone all the way to quantum networking, which is closer to what Qunnect's product line is to do. So what I'm going to talk about is the distribution of entanglement for networking. That's what Qunnect's hardware does, and we'll call that sort of version 2.0. And as hardware continues to be innovated and you go towards this larger vision of the quantum internet, you can imagine a whole new generation of stuff, which is version 3.0, which will be very exciting when we all get there, right? And just to give you an idea, when we first started as a company sort of seriously, it was at the tail end of the pandemic. And at that time, the list of other companies trying to do something in the space was very short. But now there's a whole new generation of companies, some of which were older companies doing QKD, which have now shifted their focus to do quantum internet. I'm just putting up a list of them because some of them, as you'll note from the details section, are companies which spun out of universities, probably of groups that you may be reading the papers of. I think that's one of the fun things about quantum is that we're seeing now a lot of really great, brilliant research technologies start to become commercial technologies. So I'm seeing that these slides didn't render completely correctly, but we're going to try to do the animation which is on this. Again, we do entanglement distribution networking, and what I've shown here are a number of devices which are shown as the blocks in this diagram. And those devices are chained together by fibers, which are the lines with the little squigglies on them. And in this case, there's 5 nodes in the system. And let's start off by thinking, how does entanglement distribution networking work? So the most fundamental component is a protocol called entanglement swapping. And what entanglement swapping entails is that you have 2 nodes, node A1 and A2, which have entanglement sources. Those are the little infinity signs. And at each one of those entanglement sources, you produce a pair of photons, which I'm showing is pink and blue. And you send 1/2 of the pair to a middling station, which in this case is node B1, while you store the other photon in a local memory unit. If you interfere or do a Bell state measurement at node B1, what you actually end up doing is mapping the photons which actually remain in the memories to the same entanglement state, so they are now entangled, and you've gained the information transfer from the distance between node A1 to node A2. The same thing can be done in another node, so we call these nodes elementary links. So that now you have 2 elementary links which are entangled, and now you can imagine a network which has a different hierarchical structure, so next layer, where now you take your 2 elementary links, and you can actually then release the photons to a center middling node, do a Bell state measurement, and you've managed to actually map the entanglement across the distance from the far nodes of A1 to A3. So this is what we're trying to do on real telecom fiber. It's something that, of course, the Nobel Prize in Physics that went to the groups of entanglement, Anton Zeilinger's group, showed this in a laboratory in the late 90s. To do it on real telecom with instruments which are commercially compatible is obviously challenging. But what gets even worse is that when you're trying to do it in the real world, all of these sources of noise, which have been mentioned in the 2 talks that preceded mine, come into play. And of course, what makes atoms really fantastic sensors makes them horrible to work with in things like memories, where you need to shield them from all of the stuff that they sense. So we work at room temperature. Qunnect became sort of like the little flagship product on Earth was the fact that we actually built the world's first commercial quantum memory that operates at room temperature. So we spent a lot of time thinking about how quantum, when deployed, at least in something like a communications network, is not going to work well at ultra low temperatures like millikelvin. So you need to start thinking about non-cryogenic systems. And all of the specialty cooling and vacuum infrastructure which make it work well in a lab are things which are not going to make it work well in a fiber hub. So first you need to get rid of that. Secondly, when you do that, you now want to have instruments which are low maintenance, highly stable, and now they're working in regimes where you don't exactly think of that whenever you think of working above millikelvin. Something that doesn't get as much focus, which I think is important just as a topic of discussion, is the fact that inter-instrument compatibility is something where a lot of losses happen in quantum. So it's one thing to talk about quantum instruments in isolation, but the moment that you try to interface two of them, you start to realize that if those losses compound because you're now trying to put them in many different nodes, that you basically don't have a communication system because very quickly it's too impractical. Real-world telecom fiber is in the ground, and some of it's in the cables which are spanned between poles, right? So aerial fiber. All of that is subject to different types of noise, which you need to deal with if you're going to be trying to send single photons through it. And finally, something which, of course, is highlighted in the previous two talks, is the precision of quantum instruments, right, demand really highly accurate local references. It's one of the reasons we actually like working with atoms. So we've built a whole series of support instruments, and those support instruments sit at each one of these nodes, which solve some of the problems which I'm talking about today. And the idea is that all of these will end up being put into rack systems very similar to, again, what you saw in the previous two talks, because that's what is native to sort of the fiber hub world. So these instruments, again, you can find some of these papers. That's what I have the QR codes here for. So the very first elementary set of instruments, the quantum memory, is a 2U rack-style instrument. The box in the center of the instrument houses a vapor cell, which is heated, so it's a warm vapor system. We use rubidium. We're very proud of this memory because, again, it was the first commercial memory to be launched, as far as we know, globally. We spec it at about 150 microseconds of storage time. Although on the table, if you can actually live with a little bit of bad fidelity, so at 150 microseconds, we're about 95% fidelity. If you can live with something a little less than that, you can push it up to something which is about 800 microseconds. We are coming out with a second version of the memory. We've spent a lot of time thinking about that inter-instrument loss problem. And one of the biggest problems we have is interfacing it well with an entanglement source. And I think everybody knows this, which is in a sort of research lab environment. But all of the typical entanglement sources which have been produced commercially by this time are typically SPDC sources, so spontaneous parametric down conversion sources. Those can be narrowed by external cavities, but all of that stuff is not so great. It's pretty complicated optics if you're trying to do something in a robust commercial system. It actually inspired us to make our own source. So our source actually utilizes a spontaneous four-wave mixing process, again within a vapor cell. So we're very proud of that. There's an archive paper which is out and it's being reviewed right now for peer review as well. Why we built our own source has everything to do with those interfacial losses. When you talk about SPDC sources, well, they're in some ways easier to build and certainly, well, not necessarily easier to filter, but easier to build. The problem is that in order to interface with something like an atomic memory, you need to narrow the line width. And the reason that we decided to go with the spontaneous four-wave mixing source is because they natively put out a much narrower line width photon. We're operating right now with a few hundred megahertz line width photons emanating from our source. And we're very proud to say, because we've learned some interesting atomic tricks that you can see in that archive paper, that we can actually operate with producing over 10 million pairs per second. This is another thing that is important whenever you start talking about communications. We get very spoiled with our cell phones that can stream Netflix, right? Quantum is nowhere near that type of throughput right now. But the only way that you start is to start trying to optimize on things like pair production and how high quality are the pairs which you produce. So right now, the lower bound on the fidelity of the pairs produced from our source, which are all HH plus VV polarization entangled, is about 95%. Again, we can push it in different directions like you can do in order to try to optimize different features, but it bodes very well for being able to serve us for what I'm going to show you, which is to put these things on real networks. Swapping station is just there to do bell state measurement. We have a few designs that we've been iterating on, so that's something that's not a commercial product yet, but we actually have sold commercially the source and the memory. We actually are about to deliver our fourth memory, our first one internationally, today. It's being boxed up. And on the support product side, we have, again, the need for highly precise local referencing. One of them is timing, which you heard some about in one of the previous talks. we basically are trying to extract or cherry pick all of the timing and time tag type of features and function generation from the instruments that we use in the laboratory and put it in a box, like a 1U unit. We call that QSync. It needs to be something which is, again, in the sort of picosecond accuracy. So this one runs off of White Rabbit as its background algorithm. We also need to have very highly stable references for the wavelengths of our lasers. So we developed an atomic-based reference, which locks not only the ground state near IR lasers like you would do in common SAS, but also uses a second feature to be able to lock telecom frequency lasers. And then finally, we have this interesting pair-style device that flanks every fiber, which acts in a time multiplex way to go out and to actively query the fiber for the instantaneous fidelity, and then create a compensation signal in order to correct for the noise and other types of things which happen on the fiber, which can cause problems in the communications. So we're putting everything to the test. One of the most exciting developments in Qunnect's recent world is that in December we closed our first major financing round. We were able to actually work with a commercial fiber provider to develop a test bed in New York City of existing commercial fiber. They fused different segments together, and what you can see here is we have a loop of 34 kilometers running from our test facility in the Brooklyn Navy Yard through Brooklyn and Queens. Some of the hippest neighborhoods are on top of our fiber. And then we have another set of fibers which are running from Qunnect's facility to the NYU Engineering School and then to their Center for Quantum Physics on their main campus in Washington Park. So we have a few goals this year. One of them is to show that you can actually preserve polarization qubits that you distribute over distances like the 34-kilometer loop. That in fact is completed, and I'll give you stats on that in a second. Now that we know we can do it on one loop, we're going to actually use 2 loops in order to do basic entanglement swapping protocols. So this is extremely exciting. It's going to be, to our knowledge, right, the first entanglement swapping protocol to be run over like almost 70 kilometers of real-world fiber, and certainly with polarization qubits. And then finally, we're going to keep testing ways to better how we can deliver high-rate polarization qubits that are well preserved to a specific destination, like NYU. We're always seeking partnerships, so I'll advertise that. We've really turned our current laboratory into a network research hub. So Gotham Q is on even as we speak. We have an active dashboard. Some of you probably use Grafana to project your own data in your laboratories. What we do on our dashboard right now is that we constantly measure the entanglement source, which is producing 1 near IR and 1 telecom frequency photon. The near IR photon is measured locally. The telecom frequency photon goes through the 34-kilometer network. We time tag both such that when they actually are compared at the end, we can see how many pairs were preserved after the transit through the fiber. Right now, we're producing something which is, well, we're injecting maybe about 4 million pairs per second into the fiber. Of that, because you have normal losses over fiber, we have about 13.5 dB of loss over the fibers themselves, and then we have a little bit of loss over some of our instrumentation. But we preserve about 130,000 pairs per second, which we can then test for CHSH. And we find an S value almost consistently of something around 2.7. So the pairs that come back are, very high quality entanglement. And that's largely due to that instrument that I was telling you about that actually goes out and does a time multiplex preservation on the network. So in the graph you see here that says the fidelity in the fiber channel, you're looking at about 6 hours of data for each one of the graphs. Our QAPC unit every 20 seconds tests our fiber lines for an active measurement of fidelity. If it drops below a threshold, then it runs a sequence in order to do a calibration cycle where it calculates what needs to be applied to a special crystal within the device. It's called an EEO crystal, which actually acts as like a series of phase retarders and corrects for any type of instantaneous polarization rotation that you're getting because of rush hour or temperature changes and other things that happen during the day. Because of that, we're able to maintain very high fidelity of what we're transmitting through the fiber, and that's what's giving us the very high quality pairs that are preserved at the time that we can actually test and see that they're actively entangled. The Cuber, which is on the upper left, the yellow line which you see is it moves around during the day. That's what the measurements are like when we don't use that polarization compensation. So when we do that, we can run anywhere usually from about 20 to 50% QBER, which of course is almost useless if you were trying to do quantum communications. With our QAPC device, we run routinely at 2% QBER or less, which we're extremely proud of. And as I said, we're preserving about 130,000 pairs per second over this 34-kilometer loop. That's a really fantastic rate compared to what's been shown in the literature before. Our QAPC is maintaining the fidelity at something a little over 95% most of the time, but the most impressive part of this is it's also doing it with almost 99% channel uptime. And that has to do with evolutions of the QAPC, which became faster and faster at being able to calculate and compensate. We run these things over days at a time. The most that we've had the network on is 7 days straight. During that 7 days, our source has been extremely stable because the atomic reference of that locking system also has been able to stabilize it. So this is just a first step. Again, we're just distributing entanglement right now, and then the next one will be swapping. If we compare to other experiments which have been done globally on distribution of entanglement, some of the kind of notable comparisons are to compare, for instance, the coincidence rate. You'll see that that 130,000 that I mentioned, which is here at the bottom, is significantly different than any of the other numbers which you see on other systems. There have been a number of experiments which have been performed. There's a set of submarine fiber that runs between Italy and Malta. What's nice about that is it's fairly stable. It has nothing else that's transiting on it, which is interfering with the information. There was a multi-country European effort to do some measurements on that, both at one way and then looped. So that's what two of the papers are there. There's also a very lengthy demonstration from Slovakia to Austria, which was recently published in 2022, which also has some interesting numbers. But what all of these papers did is they all understood that polarization stabilization was extremely important to be able to actually achieve high rates. So many of them started off calibrating their systems, and this continued to run until the system went out of calibration. We are actively calibrating, which is why we can keep those types of numbers with very high uptime. We, again, have a QBER, which is almost always less than 3%, which is fantastic, and we're operating at very high S values. So it's, I think, very promising for our next experiments, which will be entanglement swapping. You have to start off with high-quality pairs to be able to do that also at high rates. So we know this, and of course, we believe it's very promising. The table which I'm showing in this came from a recent archive paper, which was quoting Hertz rates in teleportation. Entanglement swapping, of course, is stepping stone to doing teleportation experiments. We believe with the 10 million pairs per second that we can produce with our source that we can probably achieve swapping rates of about a kilohertz, which will be very exciting. The fiber loss itself, of course, eats away at that, so we're probably talking about tens of hertz. But this will all be over real fiber, which is extremely exciting for doing quantum networking in the future. And again, we're using polarization qubits. Almost every experiment which has ever been done on these sorts of teleportation numbers have been using time-bin qubits. So this is our lab. We started off with 1,500 square feet in one of the buildings in the Brooklyn Navy Yard. The team was like 3 people at the time that we started hiring, which was just at the end of the pandemic. And in just a few years, we've been able to create the product suite, which you saw. We've just started, well, almost opened the 4,000 square foot expansion space on the other side of the Navy Yard. Everything's there, we just need to get the instruments there. So they're moving this week. The team grew from 3 to 16, so that seems pretty great at this point. Very proud of the hard work that everyone does. And we are hiring, so if you are an experienced optomechanical engineer and would like to live in the great Republic of Brooklyn, which is downstate, we do have an opening. And I wanted to do a special shout out to AFRL and highlight one of our success stories. So this polarization compensation device that I'm mentioning started off as a feasibility study in a phase 1 quantum collider STTR grant. And it looks nothing like it started off looking like, so that's why we do feasibility studies. It now is 2 very compact boxes, and they're so robust that we were even able to take them to the Optical Fiber Conference in San Diego. That's our chief software engineer dancing on the Qunnect mat that you see there. There's a set of fiber that runs underneath that mat that's picking up the noise from her stepping on it. And the QAPC, which are the 2 black boxes on the table, are correcting for the fiber noise that she's creating from this random sort of perturbation. We also were able to display this at a recent IC conference. where we were able to show the live dashboard of Gotham Q running the data in the background and demonstrate how this is something, again, which is feasible and in active operation. So thank you to AFRL for having the vision to do the Quantum Collider STTR call, because we certainly benefited from it, and we're very proud of the device that came from it. So happy to take any questions.
Thanks for the nice talk. It was really enjoyable. So I saw your fidelity is about 95%, I think. It's a little hard for me to read the graph. What's limiting it? What prevents you from going to, say, 3 or 4 nines of fidelity?
It's more of a choice. It's a great question. We just decided that we didn't need to run at that time. Well, I have to go back. So the way that the network is currently equipped, we're basically allowing the APC to drive the cycle, where it's checking the network, checking for the active fidelity, and then doing a calibration cycle. If we wanted to take it up to 99%, then we actually have to wait longer, because we test at this point over 16 different points on the Poincare sphere, because we're trying to correct for every polarization. That takes a lot longer if you want to do it at 99%. So we know that the fidelity, at least in our hands on this network, drops rapidly enough that every few minutes we need to do some type of calibration cycle. If we want to do it to the higher fidelities, it just ends up eating up more network uptime. So it could certainly run that way, but right now we were just sort of taking a balance point. So 99% uptime with 95% fidelity, but a little less uptime, you could keep it higher if you wanted to.
Thanks for your interesting talk. Have you defined and measured notions of entanglement specific to distributive systems? I'm asking that because it seems to me that you take the regular notion of entanglement that we use in quantum mechanics and quantum computing and transfer it to quantum networking. But it seems to me that the topology is important, the topology of the networks are important to characterize the kind of distributive entanglement.
Yeah, so I'll tell you, it's actually, the supply chain delays drive so many things these days. So the reason that our network topology is a loop is because all of our equipment sits in one lab, and it was a year to get a second set of detectors or a second set of lasers. And we wanted to get started quickly. So the topology right now is very simple for that reason, but you also will note in some of the data from some of the other comparisons with other research groups, they also use loops for the same reason. I think this is just an unfortunate stepping stone as you're trying to do something a little bit more sophisticated. The other reason people like loops is because trying to actually do timing synchronization and phase locking and other things are much easier if the instruments are physically sitting in the same room, even if the photons are running over 34 kilometers. So we obviously have dodged that bullet temporarily, but that's one of the reasons we were excited to get the network segments that run to NYU. It's going to allow us to test how well we can actually synchronize things over about 12 kilometers before we actually try to do something a little bit more sophisticated over 34 plus. And the nice thing about both systems is we have 6 fibers in both, so we can actually start playing with more sophisticated topologies. It's a great question. I just think that what we find every time we try to plug something in is that there are so many sources of noise and problems that we were not accounting for that we have to fix, that starting off simple is just where we've started, right? So the network itself has only been online since April.
But I think we can use a kind of finite topology to define different notions of entanglement, even for simple topologies. And maybe this can help to give more precise measurement.
Okay, so maybe I don't understand the question. So try me again.
Thank you.
Okay.
Yeah, thanks a lot. Very impressive results and work. I was curious about the polarization compensation, and I'm assuming it relies on using the actual quantum signals to provide compensation, or do you do it differently? And because I'm wondering if I'm guessing you need real-time communication between all communication partners, right? Is that correct?
Right, so it's a great question. Two things, right? So it time multiplexes back and forth between using classical signals for the actual probing of the fiber. So you have a choice. You can use an onboard SFP laser, or you can use an external laser to actually give a classical signal, which only is detected by classical detectors within the second unit. And then it switches back through an internal optical switch to the quantum channel. So the typical way that it runs is it decides to go out and query 16 different points along the Poincare sphere. Okay. The box which receives it knows what it should have received by Ethernet right now, so we transmit the known sequence via Ethernet. Or you could have a set of schedules. It's just our current protocol. Yeah. It then compares what it received to what it should have received. Calculates based on an optimization algorithm what it needs to do as an applied signal to an EEO crystal, which is on board in the measurement station. And then it switches from the test cycle to the quantum communication cycle. We, in our software build, had to be extremely careful, as everyone in the room knows, right? You can fry your detectors in the quantum world very easily. So if you're going to have something that sends classical pulses at any point, to make sure it's very fail-proof, so that you don't end up burning your detectors when you go back to the quantum side. So right now, we've debugged it pretty well. We feel pretty confident in it, but yeah, it's just time multiplexed right now.
Yeah, thanks.
Yeah, thank you so much. This is really interesting to see some real-world demonstrations of quantum networking. I have a question about the source. Is it only one photon that's a telecom and going through fiber, or is it both? And
it's just one right now. So
okay. And do you have plans to go to 2 photons, or both a telecom?
So this source solved a problem. Again, I didn't spend any time focused on the actual mechanics of the source, but so the quantum memory is also based on atomic vapor. The memory itself uses an EIT, electromagnetically induced transparency process, to store. That only works well in the ground states of rubidium. So we needed to have a very accurate way to create photons for storage. So what we did when we created our source is create a source that creates one photon which is perfectly attuned to the memory, and the other one which is for communication, like the little animation that I showed. It solved a problem for us because it prevents us from having to do some type of other frequency conversion to be telecom compatible. So the device itself is producing the bichromatic pair.
Mm. Thank you so much.
Yeah, thank you.
Okay, so one more speaker between us and lunch, and it's my pleasure to welcome our next speaker. He currently manages the Government Quantum Information Program for Qubitekk, a quantum networking company in San Diego. He has over 13 years experience managing Department of Defense, Department of Energy, and Department of Homeland Security programs and projects. Previously, he served 20 years in the Marine Corps at both the tactical and operational levels, including command and staff billets from battalion to corps level with 4 combat tours. Please help me welcome Mr. Scott Packard.
I always enjoy listening to Dr. Goddard. I don't necessarily relish having to follow her, nor being between you and lunch. And who knew it was harder to get to Rome, New York than it is Rome, Italy? Okay, so before I get into the meat of quantum entanglement on drones, I want to tell a little story about the importance of partnership. Several of the speakers this morning talked about the partnership that brought about this facility. About 2 years ago, I was hired by Qubitekk to manage a government program with a different military department. I found myself within 3 months of being entrenched in quantum mechanics and quantum information science, having to explain the validity of Bell's theorem to a non-technical contracting officer. This is about a year and a few months before the 3 Nobel laureates got the Nobel Prize for essentially doing that very same thing. Now, go 2 years earlier than that, when AFRL, Mike Hayduk's team, took a quantum leap of faith on a small company proposing to distribute entanglement across mobile platforms. So I think the question of quantum entanglement and why it's useful has been very eloquently answered by Dr. Goddard. But why drones? So those of you that have been following the mild mess in the Middle East, the 20 years of combat operations, who've paid attention to the innovation and the use of unmanned aerial systems in Ukraine, probably already have an idea of the role drones, unmanned aerial vehicles, and other uncrewed systems play in the battlefield. Not only are drones useful in and of themselves, but in this project, it also serves as a bit of a stepping stone for other applications, including going off to space. As I talk about the subsystems that we worked on, you can easily extrapolate the usefulness not just in terrestrial applications and low altitude UAVs. You can also see how they might apply to entanglement distribution from and to space. So I'm going to talk quickly about the technical objectives that this project covered, and I'm going to cover them rather quickly. You'll see a lot of detail on the slides. I'm not going to talk to all of those. The overarching element of this project was that these technical objectives were intertwined and iterative. They weren't sequential. You make a modification to the quantum payload, it requires a modification to the optical link. You make a change to your pointing acquisition and tracking system, or PAT system, and it requires a change to the optical link. Anything you change on the UAV system itself requires a modification to the other systems that are integral to this. This was not a project of fundamental research. This was a project that focused on a very nutty engineering problem and the integration of systems that have worked very well in laboratories or in classical optical systems that we worked very diligently to integrate in order to distribute entanglement. Okay, so first, technical objective 1, and the sub-tasks underneath that technical objective were really about building a source that would survive the perturbations of an airborne craft, the vibration, as well as the varieties of that system moving around. Our commercial entangled photon source at Qubitekk already works fairly well. We ship it around the world, you break it out of the box, you plug it in, and you start producing entangled photons. But the modifications in order to really control for vibration and the peculiarities of loading this up on an actual drone required some adjustment. The polarization compensation was, as Dr. Goddard mentioned, a particular challenge that we had to get after. Additionally, anytime you flight test with AFRL, you go through a rigorous process to validate your safety considerations, your mission profile, and all the parameters. And I really appreciate John Magliano's help with getting through that flight test plan, and his patience. Okay, now with technical objective 2, this was the design of an optical communications transmission. Now there are many very robust, very high TRL systems Optical transmission between satellites to Earth ground stations is something that's been done for a while. The challenge of, one, reducing the size and coming up with the correct sized aperture, as well as linking it to an active alignment, optical alignment system, a PAT system, was again a very, very difficult engineering challenge. Again, iterative, because you make a change to the optical link, you also have to make changes to the PAT system. Okay, technical objective 3. This was led by Dr. Warner Miller at Florida Atlantic University. He already had a basic system that was bench tested that additionally he had used to demonstrate the active alignment of the system. Once we started integrating our optical channel and putting a multiplexed quantum classical challenge channel through it, that presented it required more rigor in the precision of the alignment of the system. That required a lot of iteration. Again, because you are talking about multiple systems, for instance, with the drone, I'll talk a little bit more about this when I talk about characterization of the UAV. The drone has a position in space. The gimbal, essentially the device that's holding your PAT system and our source, also has a position in space. And the communication of those locations, that position, that XYZ access, is very critical to aligning your optical link. And any minor deviations, and of course, while that UAV is in flight, there are a lot of minor deviations. Even if you have we had a very high-end UAV that maintained station holding and had a fairly stable flight pattern, but even then, it required a lot of adjustment, dynamic alignment of the PAT system, communication between the PAT system, the gimbal, PAT system, and the drone, in order for all of those locations to be synced up and maintain that optical channel. Okay, again, the characterization of the UAV platform. This was also iterative. The unloaded UAV and the amount of vibration and its ability to maintain and hold a position in flight had to be known. And as soon as you changed any of the parameters, as soon as you put a payload on it, as soon as you put a gimbal on it, all that had to then again be recharacterized. So we went through multiple iterations characterizing the platform and the amount of vibration associated with it. Okay, we were also greatly assisted by L3 Harris, which developed a model of the system. It allowed us to vary components, see how performance would affect, or how performance would be affected as you swapped in and out components, as you changed aperture size. It also was a pretty robust model that took into account environmental considerations, turbulence effects, the effects of sunlight based on various times of day, that really helped us hone in on improvements to the system, which I'll talk about a little bit later. Okay, and then lastly, this was kind of a opportune technical objective. We had the benefit of Cedar Blue as an offshoot out of BYU to develop a design for a photonic integrated chip that we hope to eventually be able to find a fab to construct. And also hope to find the funding to find a fab to construct. Okay, so some of the technical accomplishments out of this was reduced swap of our entangled photon source and the detectors. We also set up a functioning multiplex classical quantum optical link, link that to that free space optical link to between a ground station and an aerial drone. Sorry, I don't have any video. I was out of an abundance of caution of sending a large file with an accompanying video. I held off on. If anybody wants to see it, I've got it on my phone. But we in fact did achieve a signal lock between a ground station and an aerial drone. To Dr. Goddard's point earlier, not necessarily a useful amount given the quantum bit error rate, but still a multiplex channel with an achieved lock. Okay, so where do we go from here? We certainly think that there's utility for the battlefield, for the operational environment, to distribute entanglement, both to connect quantum computers and quantum sensors, but also to add security to communications where you need the highest level of information security. We see this progressing from ground station to aerial platform, to ground station to multiple aerial platforms, as well as aerial platform to aerial platform. This provides essentially covering the last tactical mile for the warfighter, bringing both quantum edge computing, quantum sensing, network quantum sensing, as well as that security I just spoke of. Some improvements to the system that our project divulged. We saw a requirement for higher power outputs. We saw an opportunity to increase aperture size as the combination of those two will let us extend range. Our next effort will be pointed at connecting the system, the ground station, to an aerial platform at around the 100-meter range. Yeah. So the couple of the other things that we saw was updating galvanometer fast steering, updating our sorry, I'm having a tough time with the pronunciation. Basically upgrading to a fast steering mirror that is capable of faster position acquisition and tracking than the system we involved. And then we are looking at incorporating time synchronization as a path forward to connecting to a quantum memory. So what does that look like? That's a little bit of an eye chart. First of all, working towards entanglement distribution from a ground station to 2 UAVs. From there, using a small UAV as a quantum relay, either to another UAV or to a distant ground station. Taking that and transitioning to entanglement swapping, and then entanglement swapping with an included memory. Okay. So that concludes. Do I have any questions? And be gentle. That 20 years in the Marine Corps was as an infantryman, so.
Sorry, I have a quick. Thank you very much. Very impressive work. Could you comment on the resilience against noise and sort of blinding with lasers or daylight? Because those systems are quite exposed, right? And And I was just curious on that.
Yeah, I mean, a very real challenge with anything that works over free space optical is, you know, you're working, particularly with the quantum signal, you're working with very low power, you know, 2 femtowatts of power, right? So the you know, sunlight is a challenge in and of itself, notwithstanding any direct attention. One of the things you have going for you is a mobile platform that can move. You also have low probability of intercept, low probability of detect of the optical signal that make the adversaries a particular effort to do a denial of service through basically flooding the optical channel a little more challenging. But yeah, it's a very real aspect to the system is if anybody gets close enough on access to your receiver, they can flood out your you can program in responses to a loss of signal that allows you to address that.
And your current system, was that a demonstration at night or daytime?
That demonstration was inside a much smaller hangar, a warehouse that had open doors allowing incidental sunlight in. It was not full daylight, but a well-lit, more well-lit than this facility currently is.
Okay.
So.
Yeah, thank you very much.
Yep, thank you.
Hi, thank you very much. Do you have any capabilities of correcting for atmospherics?
So the model that L3 Harris built had the ability to include turbulence and ambient light and other atmospheric. It was meant to replicate the conditions you might experience in daylight during you know, outside up to a kilometer operations, and it had various you know, various scenarios in the model. Our system has polarization control or compensation in it, but as far as the degree of variability is still a work in progress, I would say.
Thank you.
If you have any ideas, I'd be happy to talk to you after my talk.
Sure. LiDAR.
Thanks for the great talk. I had actually a question about the entangled photon sources that you guys have been building. Can you say a few words on the specs of those photon sources? Like, are they narrow band or broadband? What is the rep rate of the photons?
It's narrow band. It's narrow line width, 810 nanometer spontaneous parametric down conversion, type 2. Generally about 10,000 pairs per second. And
is it cavity enhanced by any chance?
No, no. We are currently working on a cavity enhanced narrow line width source, but that works great in a lab. Not so great when you start introducing vibration into the problem set. So, in order to have a deterministic source, you need to decrease the line width.
Exactly. Thank you.
Hi, thank you. That was a really nice talk. That was interesting. I had a doubt that it's in a hypothetical situation. Suppose someone intercepts your communication from the UAV to the ground station and performs maybe an entanglement swapping in between. Are you able to detect that, or is there a security flaw in this communication?
Yeah, because in order to confirm that one of the challenges, of course, is intercepting that signal. And as soon as you intercept that signal and you've lost the signal, reestablishing the signal. Key element with QKD as any is authentication of the nodes. It's one of the fundamental concerns that the NSA had. But we have been working with folks who do PQC as a mechanism for adding more rigor to the timing channel. The quantum channel itself is inherently secure, and once you break that, once you intercept that, you've effectively broken the entanglement. But yeah, I mean, node authentication is one of the basic challenges with entanglement swapping as well. So it is a ongoing challenge. We have a project with another large defense contractor for key authentication that's meant to specifically address that particular problem.
Thank you.
Thanks for your talk. When you talk about our areas for advancement, you mentioned time synchronization for quantum memory. What do you mean exactly with quantum memory in that context?
Yeah, so I think, again, as I hate referring to Dr. Goddard's speech. Boy, it makes you want to go talk to Dr. Goddard. And we're kind of a competitor. So we agree with Qunnect that quantum memories are key to solving a number of problems, including transduction, I mean, changing modalities across the variety of quantum components. But the precise timing, we work in, I don't even know the degree of precision of our systems, but the timing synchronization in order to ensure that the qubit you're holding on in a memory is the right qubit is kind of a critical component of entanglement swapping and transduction. And so the big step is to just connect to a quantum memory. Given limitations in funding and resources and time, and also the availability of quantum memories, we think that refining time synchronization of Alice and Bob is a reasonable step given those resource limitations. All the money, all the expertise, and we would move right into quantum memories. But I think, again, as Dr. Goddard mentioned, they've sold 4 of them. They didn't sell any of them to us. So, until we can get our hands on one, we want to prep the battlefield of quantum information science and our preparedness for when quantum memories become more ubiquitous and available, so we can connect to them.
Okay, thank you.